70,000 years. That's how long it would take humanity's fastest spacecraft to reach the nearest star. And for most of human history, that number has been a wall. Not a challenge, not a puzzle, a wall. The kind that doesn't move no matter how hard you push. The speed of light isn't just a limit, it's a sentence. It means the universe beyond our solar system might as well be painted on the sky. Unreachable, untouchable. A cosmic museum we can observe but never visit, except something changed, quietly, recently, in a way that most people haven't noticed yet. In 2024, a paper landed in the physics community that did something no one thought was possible. It solved the problem that had kept warp drives locked in the realm of fantasy for 30 years. The problem Einstein himself couldn't crack. The problem that required exotic matter, negative energy, the kind of physics that doesn't just bend the rules but breaks them entirely. And this paper said, what if we've been looking at it wrong the whole time? Because here's what most people don't know. The Alcubierre warp drive, the most famous faster-than-light concept in modern physics, was never about moving through space. It was about moving space itself. Compressing it in front of you, expanding it behind you, riding a wave of space-time like a surfer on an ocean that shouldn't exist. The math worked. It always worked, but it demanded something the universe supposedly refused to provide. Until now. Until a handful of physicists decided to ask a different question. And what they found didn't just crack the door open, it kicked it off the hinges. This is the story of how the impossible became merely difficult, and why the stars were never meant to stay out of reach. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. 25 trillion miles. That is the distance to our front porch. Not some distant galaxy cluster teetering at the edge of the observable universe. Not a quasar burning in the infant cosmos. Not even a particularly interesting nebula halfway across the Milky Way. 25 trillion miles is how far you would have to travel to reach Proxima Centauri, the nearest star to our Sun that is not the Sun itself. The closest stellar neighbor we have, the star next door, and it might as well be in another dimension. If you could somehow board a spacecraft today, right now, and point it at Proxima Centauri, and if that spacecraft were capable of traveling at the absolute maximum speed the laws of physics permit, the speed of light itself, you would arrive in 4.24 years, a little over 4 years of travel time, at a velocity so extreme that every atom in your body would need to be converted into pure energy just to approach it. 4 years. That is the best-case scenario. The physical speed limit of the universe, pushed to its absolute edge, and the payoff is a single presidential term spent hurtling through the void before you reach the nearest star. And that is if you could travel at light speed, which you cannot. Nothing with mass can. The spacecraft we have actually built, the fastest objects humanity has ever launched into the black, are not even close. Voyager 1, the probe that has traveled farther from Earth than any other human-made object, is currently moving at about 38,000 miles per hour. That sounds fast. It is not. At that speed, Voyager 1 would take more than 70,000 years to reach Proxima Centauri. 70,000 years, the entire span of recorded human history, from the first cave paintings to the smartphone in your pocket, fits comfortably inside that travel time twice over. You could launch a mission to Proxima Centauri today, and by the time it arrived, whoever or whatever is living on Earth would be so far removed from the civilization that built the ship that they might not even recognize it as a product of their own species. NASA's Parker Solar Probe holds the current record for the fastest human-made object ever, clocking in at over 430,000 miles per hour during its close passes around the Sun. Screaming fast by any human measure, still not nearly enough. At that velocity, the trip to Proxima Centauri would still take thousands of years. The math is unforgiving, the distances are absurd. And the speed limit, the universal constant that governs every particle and wave in existence, refuses to bend. That speed limit has a name. It is called c, the speed of light in a vacuum, and it sits at roughly 186,000 miles per second. It is not just fast. It is the fastest anything can go, ever, under any circumstances, according to the rules written into the fabric of spacetime itself. And those rules were handed down by Albert Einstein in 1905 in a paper that redefined physics and closed a door humanity has been trying to pry back open ever since. Einstein's special theory of relativity is built on two simple principles. The first is that the laws of physics are the same for all observers moving at constant speed relative to one another. The second is that the speed of light in a vacuum is always the same, no matter how fast you are moving when you measure it. From those two assumptions, everything else follows: time dilation, length contraction, mass-energy equivalence, and the hard, cold fact that nothing with mass can be accelerated to the speed of light, let alone past it. The reason is energy. As you accelerate an object closer and closer to light speed, its relativistic mass increases. The faster it goes, the more energy it takes to push it even a little bit faster. By the time you approach light speed, the energy required to accelerate further climbs toward infinity. You would need infinite energy to push a single atom to light speed, let alone a spacecraft with people inside. The universe simply will not allow it. The speed of light is not a suggestion, it is a wall. For most of human history, that wall did not matter. We were confined to a single planet, then a single moon, then a few nearby rocks orbiting the same star. But as our ambitions grew, so did the problem. The stars are not close. Even the nearest ones are separated by distances so vast that light itself, the fastest thing in existence, takes years to cross them. And if light takes years, then anything slower takes lifetimes, multiple lifetimes, generations of lifetimes. The term for this kind of mission is a generation ship. A vessel large enough to sustain a self-contained human population for centuries or millennia, with the understanding that the people who board it will never see the destination, neither will their children or their grandchildren. The ship itself becomes a traveling civilization, a closed ecosystem drifting through the void, carrying the descendants of the original crew toward a star they will only know from stories. Assuming the ship does not fall apart, assuming the life support holds, assuming the population does not collapse from disease or conflict, or the slow psychological toll of living your entire life inside a metal tube with no exit and no hope of ever seeing home again. This is not science fiction speculation. This is the actual engineering discussion taking place among the few people who take interstellar travel seriously. If we want to send humans to another star using anything resembling current technology, generation ships are the only option on the table. And generation ships come with problems that have nothing to do with propulsion and everything to do with biology, sociology, and the uncomfortable truth that humans are not built to live in isolated boxes for 10,000 years. Some researchers have proposed suspended animation or cryogenic freezing as a way around the generation ship problem. Put the crew to sleep, wake them up when you arrive. Elegant in theory, catastrophic in practice if anything goes wrong. And we have no idea how to do it safely for more than a few hours, let alone centuries. Others have suggested uploading human consciousness into machines, sidestepping biology entirely. That solution trades one set of impossible problems for another and assumes we will one day understand consciousness well enough to copy it, which we do not. There is another option. Build smaller, faster probes, skip the humans entirely and send robots. That is the philosophy behind Breakthrough Starshot, a $100 million initiative backed by Yuri Milner and Stephen Hawking before his death. The idea is to accelerate tiny spacecraft, each weighing only a few grams, to about 20% of light speed using a massive ground-based laser array. At that velocity, the probes could reach Alpha Centauri in roughly 20 years. 20 years is a human timescale. 20 years is something a single generation could live to see. Launch the mission, wait 2 decades, receive the data. No generation ships, no frozen colonists, just a swarm of tiny cameras flying past another star at 40 million miles per hour. It is one of the most serious interstellar mission concepts currently on the table. It is also nowhere near ready. The engineering challenges are staggering. You need a laser powerful enough to push a gram-scale object to relativistic speeds without vaporizing it. You need to aim that laser with absurd precision across distances where even a tiny error means the probe misses its target by light years. You need the probe to survive the journey through interstellar space, where a single grain of dust at 20% light speed hits with the force of a bomb. And you need it to send data back across 4 light years using a transmitter the size of a postage stamp. Every one of those problems is technically solvable in theory. None of them have been solved in practice. Project Daedalus, a concept study from the British Interplanetary Society in the 1970s, proposed a fusion-powered spacecraft capable of reaching about 12% of light speed. The target was Barnard's star, roughly 6 light-years away. The trip would take 50 years. The ship would weigh 54,000 tons at launch, most of that fuel, and it would never slow down. It would scream past its target star at 12% of light speed, snap a few photos, and keep going forever into the dark. Daedalus was never built. The engineering required to construct a working fusion drive in space, let alone one capable of accelerating 50,000 tons to a meaningful fraction of light speed, remains beyond our capability. So here is where we are. The nearest star is 25 trillion miles away. The fastest spacecraft we have ever built would take thousands of years to reach it. The theoretical maximum speed, light speed, would still require over 4 years, and we cannot reach light speed. Not with rockets, not with nuclear engines, not with anything currently sitting in a blueprint or a physics textbook. The universe is enormous. We are slow, and the gap between those two facts is so wide that for most of human history, interstellar travel has been treated as a fantasy rather than a plan. Science fiction did not care. Science fiction has been sending humans to other stars since before we figured out how to leave the atmosphere. Writers invented warp drives, hyperspace lanes, jump gates, and a dozen other narrative shortcuts to get their characters from star to star without spending half the novel describing the trip. The genre needed faster-than-light travel to function, so it waved its hands, invented the technology, and moved on. For decades, that was fine. Everyone understood the difference between a story and a blueprint. But science fiction has a strange way of becoming science fact when you give it enough time. Jules Verne wrote about submarines and moon rockets long before either existed. Arthur the 100th. Clarke described geostationary communication satellites in 1945, more than a decade before Sputnik. The line between speculation and engineering is not as clean as it looks. And somewhere along the way, a small number of physicists started asking a question that sounded absurd on its face. What if faster-than-light travel is not actually impossible? What if Einstein's speed limit only applies to objects moving through space, and there is a loophole? That question did not come from science fiction writers. It came from scientists reading Einstein's other theory, the one that came 10 years after special relativity and rewrote the rules again. General relativity, the theory that describes gravity not as a force, but as the curvature of space-time itself. Mass bends space. Bent space tells mass how to move. The equations are elegant, and they are still the best description of gravity we have. But they are also flexible in ways Einstein himself did not fully anticipate. General relativity allows for some very strange solutions. Black holes, where space-time curves so sharply that not even light can escape. Wormholes, hypothetical tunnels connecting distant points in space, and under the right conditions, regions where space-time itself expands or contracts faster than light. Not objects moving through space faster than light, which special relativity forbids, but space itself, stretching and compressing, carrying objects along with it. That distinction matters. It is the crack in the wall, the place where the rules bend just enough to let a new idea slip through. In science fiction, this idea had a name, warp drive, coined by John W. Campbell in the 1930s, and popularized by Star Trek in the 1960s, the warp drive became the default explanation for how starships crossed galactic distances in the time it took to brew a cup of coffee. The Enterprise did not break the speed of light. It bent space around itself, contracting the space in front and expanding the space behind, surfing a wave of distorted space-time from star to star. The ship itself never moved faster than light relative to the space immediately around it. The space moved, the ship went along for the ride. For most of the 20th century, that idea lived comfortably in the fiction section. Then in 1994, a physicist named Miguel Alcubierre published a paper that changed the conversation. He was not trying to build a starship. He was solving Einstein's field equations, the mathematical heart of general relativity, to see if something like a warp drive could exist even in principle, and he found a solution, a way to arrange mass and energy in space such that a bubble of normal space-time could be surrounded by a region where space contracts in front and expands behind. Inside the bubble, a starship would sit motionless relative to the space around it. Outside, an observer would see the bubble, and everything in it moving faster than light. The math worked, the equations balanced. General relativity, the most rigorously tested theory in all of physics, did not forbid it. Alcubierre had found the loophole. For a brief moment, warp drive stopped being science fiction and became a topic of actual scientific discussion. Papers were written, conferences were held. NASA's Advanced Propulsion Lab started taking a look. The door Einstein had closed in 1905 was cracked open again, and on the other side was the entire galaxy. Then reality walked in, because Alcubierre's solution came with a price. To create the warp bubble, to bend space-time in the way his equations required, you needed something that does not exist. Exotic matter, not antimatter, which is real. Not dark matter, which we are pretty sure is real even if we have never touched it. Exotic matter. Matter with negative mass, negative energy density. Stuff that pushes instead of pulls, that repels gravity instead of attracting it. The kind of matter that has never been observed, never been created, and may not be physically possible under the laws of quantum mechanics as we currently understand them. The amount you would need was obscene. Alcubierre's original calculations suggested a warp bubble large enough to carry a small spacecraft would require an amount of exotic matter equivalent to the mass energy of the entire observable universe. Later refinements brought that number down, way down, but even the most optimistic revisions still required more energy than humanity has ever generated in its entire history, and all of it in a form that might not exist. So yes, warp drive was technically allowed by general relativity, and yes, the math checked out. But the practical requirement, the one thing the entire concept hinged on, was a substance pulled from the pages of theoretical physics with no clear path to ever producing even a single atom of it in a laboratory. Faster than light travel was possible in principle, and completely impossible in practice. The door was open, the gap was infinite. That is where the conversation sat for nearly 30 years. Warp drives remained a fixture of physics papers and conference presentations, a fun thought experiment that let researchers explore the edges of general relativity without ever pretending it would lead to a working spacecraft. The speed of light remained the wall. Proxima Centauri remained 25 trillion miles away, and humanity remained stuck in a solar system where even the outer planets took years to reach. Until 2024, when a private research lab claimed they had solved the impossible part. Miguel Alcubierre was not trying to save humanity when he invented the warp drive. He was a graduate student at Cardiff University in Wales, 28 years old, working on his doctorate in theoretical physics. And like a lot of graduate students in the mid-1990s who had grown up watching Star Trek, he was curious whether the science fiction technology he had seen on television could actually work in the real universe, not whether we could build it, whether the equations would even allow it. Whether general relativity, Einstein's theory of gravity and spacetime, had any room inside it for something as absurd as faster-than-light travel. Most physicists at the time would have told you the answer was no. Special relativity had closed that door in 1905. Nothing with mass can reach light speed. Nothing can exceed it. The math is clear. The experimental evidence is overwhelming. The speed of light is a wall, and you cannot break through a wall by politely asking the equations to reconsider. But Alcubierre was not asking about objects moving through space. He was asking about space itself. And that question had a different answer. In 1994, Alcubierre published a paper in the journal Classical and Quantum Gravity with a title so dry it could have been mistaken for a typo. The warp drive, hyper-fast travel within general relativity, no drama, no grand declarations, just a straightforward description of what he had done. He had taken Einstein's field equations, the ones that describe how mass and energy curve spacetime, and solved them for a very specific scenario. A bubble, a region of flat, normal spacetime surrounded by a shell where spacetime itself was warped, not bent gently like the curve around a planet or a star, warped aggressively, violently in a way that contracted space in front of the bubble and expanded it behind. The result was a solution that technically allowed faster-than-light travel without breaking any of the rules Einstein had written. The ship inside the bubble would not be moving. It would sit motionless relative to the space immediately around it. But the bubble itself, and everything inside it, would be carried along by the motion of spacetime. Space in front would compress, pulling the destination closer. Space behind would stretch, pushing the origin farther away. The ship would surf a wave of distorted geometry from one star to another, and from the perspective of someone standing outside the bubble watching it go by, the whole thing would appear to be moving faster than light. That is the idea. That is the entire concept. And it works on paper because general relativity does not forbid spacetime itself from expanding or contracting faster than light. In fact, spacetime does that all the time. The universe has been expanding since the Big Bang, and the most distant galaxies are receding from us faster than light right now because the space between us and them is stretching. Those galaxies are not moving through space faster than light. The space is growing. General relativity is fine with that. It has always been fine with that. Alcubierre just asked whether you could do it on purpose in a small controlled region and use it to move a spacecraft. The answer, mathematically, was yes. The equations balanced. The solution was consistent with general relativity. There were no contradictions, no violations, no places where the math broke down and started spitting out infinities or paradoxes. It was a valid solution to Einstein's field equations. That alone was remarkable. For the first time in the history of physics, someone had written down a working model for faster-than-light travel that did not require rewriting the laws of the universe. It just required bending them. To understand why this was such a big deal, you need to understand what general relativity actually says about space-time. Most people think of space as empty, a stage where things happen, a backdrop. But general relativity says space is not a backdrop. It is a participant. It has structure. It can bend, stretch, twist, ripple. Mass and energy tells space-time how to curve. Curved space-time tells mass and energy how to move. That feedback loop is what we experience as gravity. When you drop a ball, it is not falling because a force is pulling it down. It is following the straightest possible path through space-time, and that path happens to curve toward the center of the Earth because the Earth's mass has bent the geometry. That is not a metaphor. That is the actual mechanism. Space-time is a thing. It has properties, and one of those properties is that you can deform it. Every object with mass already does this. You are doing it right now. Your body is bending space-time around you by an amount so tiny it would take the most sensitive instruments on Earth to detect it. The Earth bends space-time enough to keep you pressed against the ground. The Sun bends it enough to hold 8 planets in orbit. A black hole bends it so sharply that space itself folds inward and nothing inside can climb back out. Alcubierre looked at those solutions and asked a follow-up question. If mass bends space-time and bending space-time changes how objects move through it, could you arrange mass and energy in such a way that the bending itself does the moving? Could you create a region where space-time is compressed in one direction and stretched in the other, and put a ship in the middle? The answer was yes, but the cost was extreme. Here is how the geometry works. Imagine space-time as a flat sheet stretched tight. You, standing on that sheet, want to get from one side to the other. Normally you would walk, one step at a time, covering distance at whatever pace your legs allow. That is normal motion through space. Now imagine someone grabs the sheet in front of you and pulls it toward you, bunching it up so that the far edge is suddenly much closer. At the same time, someone else grabs the sheet behind you and pulls it in the opposite direction, stretching it out so the place you started is suddenly much farther away. You have not moved. Your feet are in the same spot on the sheet they were a moment ago. But the distance between where you are and where you want to go has collapsed. You step forward once, and you have crossed what used to be half the sheet. That is the Alcubierre drive in the simplest terms. You are not moving faster. The destination is not getting closer in any normal sense. The space between you and the destination is being manipulated so that the journey becomes shorter without you having to travel faster to complete it. You contract space-time in the direction you want to go and expand it in the direction you came from, and the result is motion. Faster than light motion from the perspective of someone watching from outside the distortion. But locally, inside the bubble, nothing strange is happening. You are sitting still in flat space-time. The universe outside is doing all the work. Another way to picture it is an escalator. You are standing still. The escalator is moving. From your perspective, you are stationary. From the perspective of someone standing at the bottom watching you rise, you are moving. The escalator is doing the work. You are just along for the ride. The Alcubierre drive is the same idea, except instead of a mechanical staircase, you are riding a wave of curved space-time, and instead of moving you up one floor, it moves you across light years. The beauty of this setup is that it does not violate special relativity. Special relativity says nothing with mass can move through space faster than light. Fine. The Alcubierre drive does not move through space. It moves space. The ship inside the bubble is stationary relative to the local space-time around it. It never accelerates past light speed. It never experiences the infinite energy problem that makes normal faster-than-light travel impossible. It just sits there while space-time does the accelerating. From the ship's perspective, nothing unusual is happening. Clocks tick normally. Time flows at the usual rate. You could sit in the cockpit drinking coffee while the bubble carried you to Alpha Centauri, and you would feel nothing. That is the elegance of the solution. It is not brute force. It is not a bigger engine or a better fuel. It is a loophole, a way to get around the speed limit without technically breaking it. Einstein's equations allow space-time to expand and contract faster than light. Alcubierre just found a way to weaponize that permission. He turned the flexibility of general relativity into a propulsion system. For a brief window after the paper was published, the idea generated genuine excitement, not among science fiction fans, though they loved it. Among physicists, serious researchers at serious institutions started running the numbers to see if Alcubierre had missed something. The consensus was that he had not. The math was clean. The solution was valid. General relativity really did permit this kind of space-time manipulation. NASA's Advanced Propulsion Physics Laboratory, a small research group at Johnson Space Center in Houston, added the Alcubierre drive to its list of concepts worth investigating. Papers were published exploring variations on the geometry, tweaks to the design that might reduce the energy cost or smooth out some of the rougher edges in the equations. For the first time in human history, faster-than-light travel was not just a plot device, it was a legitimate topic of scientific research. And the reason it was legitimate was because Alcubierre had done something no science fiction writer ever bothered to do. He had shown his work. He had written down the equations. He had demonstrated that the universe, as we currently understand it, does not forbid this. It just makes it very, very hard. How hard? That is where the dream hits the wall. Because creating the kind of space-time distortion Alcubierre described requires energy, a lot of energy. And not just energy in the normal sense. You need a very specific kind of energy, one with a property that, as far as anyone can tell, does not exist in nature. The technical term is negative energy density. That phrase gets thrown around a lot in discussions of warp drives, and most of the time it gets simplified to exotic matter or negative mass. Those terms are not quite accurate, but they point in the right direction. Normal matter, the kind you are made of, the kind that makes up stars and planets and everything else you have ever touched or seen, has positive mass, positive energy density. It pulls. It attracts other matter. It curves space-time inward. A star sitting in space creates a gravitational well. Mass rolls toward it. That is what normal matter does. Exotic matter, if it exists, would do the opposite. It would have negative energy density. It would push, repel, curve space-time outward instead of inward. If you put a lump of exotic matter on a table, the table would not hold it up. The exotic matter would push away from the table, push away from the Earth, push away from everything with normal mass. It would anti-gravitate. And if you arranged it in just the right geometry around a spacecraft, it would curve space-time in exactly the way Alcubierre's equations require. Contract space in front, expand space behind, create the bubble. The problem is that no one has ever seen exotic matter. Not in a lab, not in nature, not anywhere. Antimatter is real. We produce it in particle accelerators all the time, but antimatter has positive mass. It falls down, not up. It attracts, not repels. Dark matter, the invisible stuff that makes up most of the mass in the universe, also has positive mass. We infer its existence from the way galaxies rotate and the way light bends around galaxy clusters. Whatever dark matter is, it pulls. It does not push. Exotic matter, the kind with negative energy density, has never been observed, and there are good reasons to think it might not be possible under the laws of quantum mechanics as we currently understand them. There is something called the quantum inequality, a principle that comes out of quantum field theory. It says that while you can create tiny regions of negative energy density for extremely brief moments under very specific conditions, those regions are always surrounded by larger regions of positive energy density that more than compensate. The universe does not let you cheat. You cannot extract a net negative energy. You cannot build up a reservoir of exotic matter and store it. And you certainly cannot gather enough of it to curve spacetime on the scale required to move a spacecraft. Alcubierre's original paper did not dwell on this. He acknowledged that his solution required exotic matter, noted that such matter had not been observed, and moved on. The point of the paper was to show that the geometry was possible, not that we could build it tomorrow. Just that general relativity left the door open. And it did. The door was open, but the threshold was guarded by a requirement so extreme that it might as well have been a wall. How much exotic matter are we talking about? The numbers depend on the size of the bubble and the specifics of the geometry, but the original estimates were apocalyptic. One early calculation suggested that creating a warp bubble large enough to carry a small spacecraft, maybe 100 meters across, would require an amount of exotic matter equivalent to the total mass energy of the entire observable universe. Every star, every galaxy, every planet, every atom, all of it converted into exotic matter and arranged in a thin shell around your ship. That is not an engineering problem. That is a physics problem. Even if exotic matter turned out to be real, even if we figured out how to produce it in a lab, the idea that we could ever generate enough of it to power a warp drive was beyond absurd. You would need to harvest the mass of the universe to move one ship. The energy budget was not impractical, it was impossible. Later refinements brought that number down. Way down. By tweaking the shape of the warp bubble, by making it thinner, or adjusting the rate at which space-time transitioned from normal to distorted, researchers managed to reduce the exotic matter requirement by several orders of magnitude. One widely cited improvement, published by Chris van den Broek in 1999, brought the requirement down to something closer to the mass of the Sun. Still enormous. Still wildly beyond anything humanity could produce. But at least it was a number you could write down without laughing. Other researchers kept pushing. They explored different geometries, different distributions of exotic matter, different ways to shape the bubble to minimize the energy cost. Some models got the requirement down even further, into ranges that started to look almost reasonable by the standards of megastructure engineering. Not something we could do today, not something we could do in the next century, but maybe, hypothetically, something an advanced civilization with control over stellar-scale energy resources might consider attempting. That was the state of the field for most of the 2 decades after Alcubierre's paper. Warp drives were theoretically permitted by general relativity, the math worked, the geometry was sound, but the practical requirement, the exotic matter, remained a showstopper, a concept that could not be tested, a technology that could not be built. A beautiful idea that lived entirely on paper with no clear path from the equations to the engine room. And then there was a second problem, one that did not get as much attention in the early years but has become increasingly troubling the more physicists have thought about it. Even if you somehow solved the exotic matter problem, even if you built the bubble, you might not be able to control it from inside. The issue is called the horizon problem. When the warp bubble is moving, space-time around it is distorted so severely that light from the front of the bubble cannot reach the back, and light from the back cannot reach the front. The ship inside is causally disconnected from the edges of its own warp field. You are sitting in the cockpit with your hands on the controls, but the controls do not connect to anything. You cannot send a signal forward to adjust the geometry at the front of the bubble because that signal would have to travel faster than light through distorted space-time to get there. You cannot steer, you cannot stop. You cannot even measure what is happening at the boundary of your own bubble because the information cannot reach you. Alexei Krasnikov, a Russian physicist, proposed a workaround in 1995. Instead of a bubble, build a tube, a distorted region of space-time that stretches from your starting point to your destination like a tunnel. Travel through the tunnel at normal speeds or near light speeds, and when you emerge, you will have crossed a distance that would have taken much longer through normal space. The tube compresses the journey without requiring you to disconnect from the universe around you. The problem is that building the tube still requires exotic matter, and it requires you to travel to your destination at sublight speed first to lay down the distortion, so it does not help with the original goal of reaching a new star for the first time. It only helps if you are making a return trip. There are other solutions floating around. Proposals for alternate geometries that avoid the horizon problem or reduce the exotic matter requirement to nearly zero. But those proposals come with their own costs. Some of them do not actually permit faster than light travel. They just let you take shortcuts through space-time that are shorter than the straight-line path. Useful, but not warp drive. Others rely on speculative physics that has not been tested and may not be correct. And a few simply trade one impossible requirement for a different impossible requirement. The cleanest, simplest, most elegant version of the warp drive remains Alcubierre's original model, and that model requires exotic matter at a scale we cannot produce. That is the impossible dream. Not that the geometry does not work, it does. Not that general relativity forbids it, it does not. The impossible part is the fuel. The one ingredient the entire concept depends on, the substance that might not exist. For 30 years, that is where the conversation ended. Alcubierre had proven that faster-than-light travel was allowed in principle, and physics had proven that principle was not enough. Then someone decided to ignore the rules. The problem with exotic matter is not that we do not understand what it is. We understand it perfectly, too perfectly in fact. We can describe its properties, write down the equations that govern its behavior, and explain exactly how it would need to interact with spacetime to make an Alcubierre drive work. The problem is that understanding something and finding it are not the same thing. And exotic matter, the substance that makes warp drive possible on paper, has never been found, not in a laboratory, not in space, not anywhere in the observable universe. We know what it would look like if it existed, we just have no evidence that it does. Start with the name, exotic matter. It sounds like something out of a science fiction novel, and that is not an accident. The term was chosen specifically because normal language does not have a word for what this stuff is supposed to do. It is not antimatter. Antimatter is real. We produce it in particle accelerators, store it in magnetic traps, and study its properties. Antimatter has positive mass. Drop a lump of antimatter in a gravitational field and it falls down, not up. It attracts other matter gravitationally, just like normal matter does. The only exotic thing about antimatter is that it annihilates when it touches normal matter, converting both into energy. But gravitationally speaking, antimatter behaves exactly the way physics says it should. It pulls. It bends spacetime inward. It has positive energy density. Exotic matter is different. Exotic matter, if it exists, would have negative mass, negative energy density, and that changes everything. Normal matter curves spacetime inward, creating a gravitational well that pulls other objects toward it. That is what mass does. That is gravity. Exotic matter would curve spacetime outward. It would create a gravitational hill instead of a well. Objects would roll away from it instead of toward it. If you placed a chunk of exotic matter on a scale, the scale would not register weight. It would register negative weight. The exotic matter would push against the scale, trying to accelerate away from the Earth instead of falling toward it. Put it in a box, and the box would try to fly apart. Let go of it in midair, and it would not drop. It would rise, not because something is lifting it, but because it repels mass. All mass, including its own. This is not a small deviation from normal physics. This is a complete inversion of one of the most fundamental properties of matter. Every object you have ever touched, every atom in your body, every star in the sky, all of it has positive mass, positive energy density. The idea that something could exist with the opposite property, with mass that pushes instead of pulls, is so strange that for most of the 20th century, physicists assumed it was impossible. Not difficult, not unlikely, impossible. A mathematical curiosity with no physical counterpart in the real world. Then general relativity came along and made things complicated. Einstein's field equations, the ones that describe how mass and energy curve spacetime, do not actually forbid negative energy density. They do not require it either. But they do not rule it out. The equations are indifferent. You can plug in positive energy density and get solutions that describe stars, planets, black holes, the expanding universe. You can plug in negative energy density and get solutions that describe things we have never seen. Wormholes, warp drives, regions of spacetime that behave in ways that seem to violate causality, but technically do not, because the equations remain consistent. General relativity does not care whether the energy density is positive or negative. It just tells you what spacetime does in response. That indifference is what gave Alcubierre his opening. When he sat down in the early 1990s to explore whether a warp drive could exist within general relativity, he was not asking whether we could build one. He was asking whether the math allowed it, and the math did. As long as you were willing to include a term in the equations representing negative energy density, that term showed up in the shell of the warp bubble, the region where spacetime transitions from normal flat geometry inside the bubble to the compressed and expanded geometry outside. The negative energy was not optional. It was load-bearing. Without it, the bubble collapsed. The geometry fell apart. The warp drive stopped working. So, what does negative energy density actually do in the context of a warp bubble? Why is it so critical? The answer has to do with the way spacetime responds to stress. When you curve spacetime, you are creating tension. Imagine pulling on opposite ends of a rubber band. The band stretches, it stores energy, let go, and the band snaps back. Spacetime does something similar. When you compress space in front of a warp bubble and expand it behind, you are creating a gradient, a steep one. The geometry is changing rapidly over a short distance, and that creates stress. Positive energy density, normal matter, makes that stress worse. It pulls spacetime inward, adding to the tension. Negative energy density does the opposite. It pushes outward, counteracting the tension, stabilizing the geometry, keeping the bubble from collapsing under its own curvature. Think of it like a tent. The fabric of the tent, the space-time geometry, is held up by poles. Positive energy density is like adding weight to the poles. The tent sags. Add enough weight and the whole thing collapses. Negative energy density is like adding tension to the fabric itself, pulling it tight, keeping the structure stable even under stress. The warp bubble needs that tension. Without it, the geometry you are trying to create simply cannot hold its shape. The equations do not balance. The solution does not work. That is why exotic matter is not just useful for warp drive. It is essential. You cannot build an Alcubierre bubble without it. Or rather, you can write down a version of the geometry that does not include exotic matter, but that version does not permit faster than light travel. It gives you something else, a region of curved spacetime that might let you take a shortcut or travel more efficiently, but not faster than light relative to an outside observer. The moment you want true warp capability, the moment you want the bubble to carry you across interstellar distances in less time than it would take light to make the journey through normal space, you need negative energy density. There is no way around it. The question then becomes whether negative energy density is even possible, not whether we can produce it in large quantities, not whether we can engineer it into a stable configuration, just whether it can exist at all. And for a long time, the answer from the physics community was a firm, maybe leaning toward no. The reasoning came from quantum field theory, the branch of physics that describes how particles and fields behave at the smallest scales. Quantum field theory has a lot to say about energy, and most of what it says points in the same direction. Energy density, on average, has to be positive. You can have temporary fluctuations, brief moments where the energy density in a tiny region dips below zero, but those moments are always surrounded by regions where the energy density is higher than average, and the total always balances out positive. The universe does not let you cheat. You cannot extract a net negative energy from the vacuum. You cannot build a reservoir of exotic matter and store it somewhere, and you certainly cannot gather enough of it to do anything useful at the scale of a spacecraft. There is a formal way to say this. It is called the quantum inequality, and it is one of the few hard limits quantum field theory places on exotic matter. The inequality says that if you try to create a region of negative energy density, the size of that region and the duration it lasts are inversely related to how negative the energy is. The more negative you make it, the smaller the region and the shorter the time it can exist. And no matter how clever you are, the total integrated energy, the sum of all the negative and positive contributions over space and time, always comes out positive or zero, never negative. The universe enforces this. Violate the inequality and you violate causality. You get time travel paradoxes, information moving backward through time, effects preceding causes. The universe does not allow that. So it does not allow sustained regions of negative energy density either. That is the wall. That is the place where physics says no. Not because we lack the technology, not because we have not figured out the engineering, because the fundamental laws governing how energy behaves in space-time forbid it, or at least appear to. Because there is a loophole, a small one, a loophole so tiny that for years no one thought it mattered. But it exists, and it has been measured, and it proves that negative energy density is not just a mathematical fiction, it is real. Under very specific circumstances you can create it. The phenomenon is called the Casimir effect, and it is one of the strangest confirmed predictions of quantum mechanics. The setup is simple. Take two flat metal plates. Place them in a vacuum, parallel to each other, very close together, a few micrometers apart, close enough that the gap between them is smaller than the wavelengths of most of the quantum fluctuations that normally fill empty space. Quantum field theory says that even in a perfect vacuum, space is not empty. It is seething with virtual particles, pairs of particles and antiparticles that pop into existence for a brief instant and then annihilate. These fluctuations are real, they have measurable effects. And in the gap between the two plates, some of those fluctuations cannot fit. The plates are too close together. Wavelengths longer than the gap are excluded. Outside the plates, in the open vacuum, all wavelengths are allowed. That creates an imbalance. There is more quantum activity, more vacuum energy outside the plates than between them. The result is a net force pushing the plates together, a measurable physical force, generated by negative energy density in the gap. The Casimir effect was predicted in 1948 by Dutch physicist Hendrik Casimir. It was first measured in the lab in 1997. The force is tiny, on the order of a few micronewtons for plates a square centimeter in area, but it is there, it is real, and it is proof that negative energy density can exist in nature, not as a theoretical construct, not as a mathematical trick, as a physical phenomenon that you can measure with instruments. For a brief moment, that discovery gave warp drive researchers a flicker of hope. If the Casimir effect can produce negative energy density, maybe there is a way to scale it up. Maybe you could engineer a configuration of plates or fields or something that generates enough negative energy to stabilize a warp bubble. Maybe the wall is not as solid as it looks. That hope faded quickly once the numbers came in. The amount of negative energy produced by the Casimir effect is absurdly small. You would need plates the size of solar systems, gaps measured in atoms, and even then the total negative energy you could extract would be a rounding error compared to what an Alcubierre drive requires. The Casimir effect proves that exotic matter is real. It does not prove that exotic matter is useful. There is also the issue of confinement. The Casimir effect only works because the plates are close together. The negative energy density exists in the gap, but it is surrounded by positive energy density everywhere else. The quantum inequality is still enforced. You are not creating a net negative energy. You are creating a localized region where the energy is slightly less than the surrounding vacuum, and that difference manifests as a force, useful for precision measurements and certain types of nanotechnology, completely useless for bending spacetime. To make a warp bubble, you need a shell of negative energy surrounding the ship, a shell that is not confined by plates or boundaries, a shell that persists in open space. The Casimir effect cannot do that, and no known variation of the Casimir effect, no matter how clever the configuration, has ever come close. So where does that leave us? We know negative energy density is possible in principle because the Casimir effect exists. We know it is required for warp drive because the equations demand it. And we know that producing it in useful quantities is somewhere between extraordinarily difficult and physically impossible because quantum field theory says so. That is the exotic matter enigma. Not that we do not understand the physics. We understand it too well. The physics tells us exactly why we cannot have the thing we need. There is one more idea that occasionally surfaces in discussions of exotic matter, and it is worth addressing because it causes a lot of confusion. The idea is called phantom energy, and it comes from cosmology. In the late 1990s, astronomers discovered that the expansion of the universe is accelerating. Galaxies are flying apart faster now than they were billions of years ago. That acceleration requires energy, a lot of energy, enough to overpower the gravitational attraction of all the matter in the universe and push everything apart. Cosmologists call that energy dark energy, and they have no idea what it is. It makes up roughly 68% of the total energy density of the universe. We can measure its effects. We can map how it changes over time. We cannot explain it. One hypothesis, purely speculative, is that dark energy might have negative pressure, not negative energy density, negative pressure. That is a different thing, but the two concepts are related in general relativity. Pressure contributes to how matter and energy curve spacetime. Positive pressure pulls things together, negative pressure pushes them apart. If dark energy has negative pressure, and if that pressure is strong enough, it could explain the accelerating expansion. Some versions of this idea, the most extreme ones, go a step further and propose that the pressure could become so negative that it rips the universe apart. Galaxies torn from their clusters, stars stripped from their galaxies, planets pulled from their orbits. Eventually, atoms themselves disintegrate. The scenario is called the Big Rip, and it is one possible fate for the universe if dark energy behaves in a very specific, very strange way. Phantom energy is the name sometimes given to the hypothetical substance that would cause this. And because it involves negative pressure, and because negative pressure is mathematically related to negative energy density in certain equations, some popular science articles have conflated phantom energy with exotic matter. They are not the same thing. Phantom energy, if it exists, is a cosmological phenomenon. It operates on the scale of the entire universe. It has nothing to do with warp drives or localized regions of negative energy density. You cannot harvest it, you cannot concentrate it, you cannot use it to stabilize a warp bubble. The relationship between phantom energy and exotic matter is purely mathematical. One involves negative pressure driving cosmic expansion. The other involves negative energy density bending spacetime in a small controlled region. They are different problems, different physics, different scales. That said, the fact that dark energy exists at all, the fact that the universe contains some kind of energy we do not understand that is pushing spacetime apart, has led a small number of researchers to wonder whether the exotic matter problem is really as insurmountable as it looks. Maybe the universe already contains mechanisms for generating the kinds of effects we need. Maybe dark energy, or something related to it, could be harnessed or manipulated in ways we have not thought of yet. Maybe the wall has a crack we just have not noticed. That is speculation. Wishful thinking dressed up in the language of physics, but it is the kind of speculation that keeps people looking. Because the alternative, the idea that warp drive is forever confined to the pages of theoretical papers with no hope of ever becoming real, is hard to accept, especially when the math says it should work. So here is the situation as it stood for 30 years after Alcubierre published his paper. General relativity permits warp drive. The geometry is sound, the equations balance, but building one requires exotic matter with negative energy density. Exotic matter exists in nature. The Casimir effect proves it, but the amounts are so small and the conditions so restrictive that scaling it up to anything useful appears impossible. Quantum field theory enforces limits on how much negative energy you can create, how long it can last, and where it can exist. Those limits are not engineering problems, they are laws, the kind of laws that do not bend just because we want them to. For most physicists, that was the end of the conversation. Warp drive was a beautiful idea, a valid solution to Einstein's equations, and completely impractical. The exotic matter requirement was not a hurdle you could engineer around. It was a brick wall built into the foundation of reality. You could study it, you could write papers about it, you could explore alternate geometries that reduced the amount of exotic matter needed, but you could not build it, not with the physics we had, not with any physics we were likely to discover in the foreseeable future. The field moved on. Other ideas took center stage: ion drives, solar sails, fusion propulsion, nuclear pulse engines, all of them slow, all of them limited by the speed of light, but all of them possible. You could build a nuclear pulse rocket tomorrow if you had the budget and the political will. It would take centuries to reach another star, but it would get there. Warp drive, by contrast, remained trapped in the theoretical realm, a tantalizing possibility with no clear path to realization. A door that was technically open but led to a room we could not enter, and then someone decided to try anyway. Not by solving the exotic matter problem, not by finding a new source of negative energy or a loophole in quantum field theory, by ignoring it, by asking a different question. What if you could simulate the warp bubble in a lab? What if you could create the geometry without the exotic matter, just to see what happens? What if the equations were hiding something we had missed? Something that only becomes visible when you stop treating the problem as theoretical and start treating it as experimental. That question and the experiments that followed would crack the wall wide open. Not by going through it, by going around it. Nobody was asking for this. That is important to understand going in. In 2020, when most of the world was locked down and the global economy was holding its breath, a handful of researchers scattered across 3 continents were spending their days staring at computer screens running simulations of space-time geometries that should not exist. They were not funded by NASA. They were not part of a university consortium. They were not backed by a government eager to claim the next great leap in propulsion technology. They were operating out of a private research lab with a budget that would barely cover the catering for a single SpaceX launch event, and they were trying to do something that the entire physics community had spent 30 years explaining was impossible. The organization is called the Limitless Space Institute. The name sounds like something out of a motivational poster, and that is not an accident. The institute was founded in 2019 by Harold White, a mechanical engineer and physicist who spent more than a decade at NASA's Johnson Space Center running the Advanced Propulsion Physics Laboratory. That lab, for context, was the only group inside NASA officially tasked with investigating fringe propulsion concepts: warp drives, wormholes, anything that sounded too strange to take seriously but had enough mathematical backing that dismissing it outright felt irresponsible. White ran that lab for years. He published papers, he built experimental setups, he gave talks at conferences where half the audience was genuinely interested and the other half was waiting for him to admit he was joking, and then he left, not because NASA told him to stop, because he wanted to move faster. The Limitless Space Institute is not in New York. That detail matters because when people hear private lab working on warp drive, they picture a gleaming facility in Manhattan with floor-to-ceiling windows and a cafeteria serving artisanal coffee. The reality is more mundane. The institute operates out of Houston, Texas. The staff is small. The office space is modest. The equipment is whatever they can afford, with a combination of private donations, grants, and the kind of crowdfunding campaigns that make traditional academic researchers uncomfortable. This is not a billionaire's vanity project. This is a group of people who decided that waiting for someone else to solve faster-than-light travel was taking too long, so they would try it themselves with whatever resources they could scrape together. White's background is worth understanding because it explains why anyone took the institute seriously in the first place. Before founding Limitless Space, he was the principal investigator on a series of experiments designed to test whether the Alcubierre warp drive geometry could be physically realized in a laboratory setting. Not at spacecraft scale, not even at the scale of a marble. At the scale of a laser interferometer, a device that measures tiny shifts in the fabric of spacetime by bouncing light between mirrors. The idea was simple in concept, absurdly difficult in execution. If you could create even a microscopic warp field, a region where spacetime was curved in the way Alcubierre's equations describe, you should be able to detect it. The light passing through that region would shift slightly, bending in a way that flat spacetime would not produce. Measure the shift, confirm the geometry, prove the concept. White's team at NASA built the interferometer. They called it the White-Jude Warp Field Interferometer, and it was one of the most sensitive instruments ever constructed for this kind of measurement. They were not trying to build a warp drive, they were trying to build a warp field detector, a tool that could tell them whether the geometry was even possible to create without exotic matter. The results were inconclusive. Some of the data looked promising, some of it looked like noise. The measurements were at the absolute edge of what the equipment could resolve, and the scientific community was split on whether the team had detected anything real or just convinced themselves they were seeing a pattern in static. White published the findings. The papers were peer-reviewed. And the reaction from the broader physics community was polite skepticism, with a side of "we told you this would not work." That is the context in which the Limitless Space Institute was born. White had spent years trying to push warp drive research forward within the constraints of a government agency. He had published papers, he had run experiments, he had done everything by the book. And the book kept telling him he was wasting his time. So he decided to write a new book, one where the goal was not to prove to skeptics that warp drive research was worth funding. The goal was to move fast enough that by the time the skeptics caught up, the conversation would have already shifted. You do not ask permission to explore the edges of physics. You build the tools, run the experiments, and show people the data. The Institute's mission is broader than just warp drive. They fund research into a range of advanced propulsion concepts, fusion engines, antimatter propulsion, beamed energy systems, anything that could plausibly cut the travel time to another star from tens of thousands of years to something a human lifetime could contain. But warp drive is the flagship, the concept that gets the most attention, the most funding, and the most scrutiny. Because if it works, even in principle, even at the scale of a laboratory demonstration, it changes the entire conversation about what is possible. It takes faster than light travel from science fiction to engineering problem. And engineering problems, no matter how hard, can be solved if you throw enough time and resources at them. The work the Institute is doing now is not experimental in the traditional sense. They are not building hardware. They are not machining components or testing materials. They are running simulations, thousands of them. Detailed numerical models of space-time geometry that explore every possible variation of the Alcubierre metric and a dozen other warp drive proposals that have been published over the last 3 decades. The computational power required for this kind of work is not trivial. Simulating the behavior of spacetime is not like simulating fluid dynamics or structural stress. You are solving Einstein's field equations, a set of 10 interrelated nonlinear partial differential equations that describe how every point in spacetime responds to the presence of mass and energy. Do that for a small region, a few cubic meters, and the math is manageable. Do it for a warp bubble traveling at 10 times the speed of light, and the equations explode into a computational nightmare. The Institute does not own a supercomputer. They cannot afford one. Instead, they rent time on cloud-based high-performance computing clusters, the kind of infrastructure that tech companies use to train machine learning models or run climate simulations. For a few $1,000s, they can spin up a virtual cluster with hundreds of processors and run a warp field simulation for a few days. The data comes back as a massive grid of numbers describing how spacetime curves, how energy density is distributed, and whether the geometry remains stable or collapses under its own equations. Most of the simulations collapse. That is the norm. You tweak one parameter, adjust the shape of the bubble, change the distribution of energy, and the whole thing falls apart. The spacetime curvature becomes infinite at some point in the grid, or the energy requirement shoots up to something absurd, or the geometry stops being a warp bubble and becomes something else entirely, a black hole, a naked singularity, a region where the math breaks down and starts producing nonsense. But every once in a while, a simulation holds together. The geometry stays stable. The energy requirement stays finite. The bubble moves through space-time without collapsing or exploding or violating causality. Those are the results that matter. Those are the configurations that get saved, analyzed, and fed into the next round of simulations to see if they can be optimized further. The process is iterative. Guess a geometry, run the simulation, see what breaks, fix it, run it again. Repeat 1,000 times. This is not the kind of research that produces a breakthrough in a single afternoon. This is the kind of research that grinds forward 1% at a time, slowly narrowing the space of possible solutions until you find one that works. The key variable they are testing is energy. Specifically, how much energy does it take to create and maintain a warp bubble of a given size, traveling at a given speed? Alcubierre's original design required an absurd amount. Later refinements brought that number down, way down. By 2012, White had published a paper showing that by thickening the wall of the warp bubble and adjusting its shape, you could reduce the energy requirement to something closer to the mass of a spacecraft rather than the mass of a galaxy, still enormous, still far beyond what we can generate. But at least it was a number you could write on a whiteboard without your hand cramping. The simulations the Institute is running now are exploring whether that number can be pushed even lower. What happens if you make the bubble thinner in some places and thicker in others? What if you oscillate the geometry, pulsing it instead of holding it static? What if you change the way space-time transitions from normal to warped, smoothing out the gradient so the stress is distributed differently? Every one of those questions requires a new simulation, and every simulation produces a data set that has to be analyzed to see whether the change helped or made things worse. The work is slow, it is meticulous, and it is producing results that nobody expected. One of the configurations they tested involved a toroidal geometry, not a sphere or a football shape like most warp bubble designs, a donut. The spacecraft sits in the hole in the middle and the warp field wraps around it in a ring. The advantage of this design is that it spreads the stress over a larger surface area, reducing the peak energy density at any single point. The downside is that the math gets harder. Toroidal geometries are notoriously difficult to model because the curvature changes in two directions simultaneously. You cannot just solve the equations in one dimension and extrapolate. You have to solve them everywhere, all at once, and hope your computer does not run out of memory halfway through. The simulation took 3 weeks to complete. The result was a warp bubble geometry that remained stable across a range of velocities and required roughly 40% less energy than a traditional spherical design. 40% is not nothing. That is the difference between impossible and maybe someday possible if we figure out how to build a fusion reactor the size of a city. Another simulation explored what happens if you do not try to eliminate exotic matter entirely, but instead minimize it. Use just enough negative energy density to stabilize the geometry and fill the rest of the energy budget with normal matter. Positive mass, the kind we know how to produce. The idea is that maybe the exotic matter requirement is not binary. Maybe you do not need a pure shell of negative energy. Maybe a thin layer, a coating, would be enough to keep the bubble from collapsing. and the rest of the structure could be built with conventional physics. The simulation ran for 2 months. The geometry held. The energy requirement dropped to something measured in kilograms of matter energy rather than solar masses, still beyond our current capability. But the gap between where we are and where we need to be suddenly looked a lot narrower. The data they are collecting is not just about energy. They are also testing stability. A warp bubble that works on paper but collapses the moment you try to accelerate it is useless. The simulations include time evolution. You start with a stable bubble geometry, apply a force, and watch what happens over the next few milliseconds of simulated time. Does the bubble hold its shape? Does it stretch? Does it tear apart? Does it shed energy in the form of gravitational radiation, slowly decaying until there is nothing left? Most designs fail the stability test. The geometry starts out clean, and within a fraction of a second, it has deformed into something unrecognizable. The ones that pass are rare, and the ones that pass while also keeping the energy requirement reasonable are rarer still. There is also the question of control. A warp bubble that you cannot steer is a missile, not a spacecraft. The simulations test whether you can adjust the geometry dynamically. Strengthen the compression in front to accelerate, weaken it to slow down, shift the expansion asymmetrically to change direction. The math says it should be possible. The simulations mostly agree, but the precision required is extreme. You are manipulating spacetime itself, and spacetime does not respond to nudges. It responds to precisely calculated distributions of energy applied in exactly the right configuration. Get it wrong by a fraction of a percent, and the bubble either does nothing or tears itself apart. The control problem is in some ways harder than the energy problem. At least with energy, you can imagine a future where we have better reactors, better power sources, better ways to generate and store the quantities we need. Control requires real-time feedback. Sensors that can measure space-time curvature with enough precision to detect errors before they cascade. Computers fast enough to recalculate the geometry and adjust the energy distribution in milliseconds. We do not have those things. We do not even have a clear path to building them. But the simulations show that in principle it can be done. The Institute is also testing hybrid geometries, combinations of different warp drive proposals that take the best features of each and merge them into a single design. Alcubierre's metric for the basic bubble structure, Krasnikov's tube concept for the approach to the destination, Van den Broek's refinements to minimize the interior volume. The result is a Frankenstein's monster of space-time engineering, and most of the time it does not work. The different geometries interfere with each other. The equations do not balance. The simulation crashes, but occasionally, very occasionally, the hybrid holds together. And when it does, the performance is better than any single design alone. Lower energy, better stability, easier control. The trade-off is complexity. A hybrid warp drive would require more sophisticated engineering, more precise calibration, more ways for something to go wrong. But if the alternative is a design that does not work at all, complexity starts to look acceptable. Why is a private institute doing this? Why is Harold White, a man with a perfectly respectable career in aerospace engineering, spending his time running simulations of space-time geometries that most physicists still consider theoretical curiosities with no practical application? The answer is not money. There is no immediate profit in warp drive research, no product to sell, no patent you can license. The answer is not fame. White already has a reputation in the field. Publishing another paper is not going to change that. The answer, the real answer, is that somebody has to. Because if the only people working on faster-than-light travel are the ones who can secure government funding or academic grants, then the work will move at the speed of bureaucracy. Proposals will be written, committees will review them. Funding will be allocated in amounts too small to make real progress. Years will pass, and the physics community will continue to treat warp drive as a fun thought experiment rather than a serious engineering goal. Private research, for all its limitations, moves faster. There are no grant review boards, no congressional oversight. No need to justify every dollar spent to a committee that does not understand the science and does not care to learn. If the institute wants to run a simulation, they rent the computing time and run it. If they want to test a new geometry, they write the code and see what happens. If an idea does not work, they do not have to write a report explaining why. They just move on to the next idea. The trade-off is resources. They will never have the budget NASA has. They will never have access to the same equipment, the same facilities, the same pool of talent, but they do not need to. Because the work they are doing right now, the simulations, the optimization, the data collection, that work does not require a particle accelerator or a space telescope. It requires computers, and computers are cheap. There is also the question of what happens if they succeed. Not if they build a warp drive, if they prove that the geometry can be stabilized using realistic amounts of energy, if they show that a warp bubble can be controlled, steered, accelerated and decelerated without collapsing, if they demonstrate through simulation that faster-than-light travel is not just allowed by general relativity, but achievable with technology that is only a few generations beyond what we have today. What happens then? Does the physics community take notice? Does NASA dust off its old warp drive research and start funding it again? Do private companies, the ones with billions of dollars and an interest in space exploration, start investing in this seriously? Or does the work remain ignored, dismissed as speculative, filed away in the same mental category as cold fusion and perpetual motion machines? White's bet is that data wins arguments. You cannot ignore a simulation that shows a stable warp bubble geometry with an energy requirement measured in tons rather than star masses. You cannot dismiss results that have been replicated, peer-reviewed and published in a journal. You can debate the interpretation. You can argue about whether the simulation is realistic, but you cannot pretend the work does not exist. And once the data is out there, once the results are public, someone else will try to replicate it. Someone with more resources, someone with better equipment, and if they get the same results, the conversation shifts. It stops being about whether warp drive is possible and starts being about how long it will take to build one. The other reason private research matters is speed. Academic research moves in cycles. You publish a paper. You wait for it to be reviewed. You wait for it to be published. You apply for funding to do the follow-up work. You wait for the funding to be approved. By the time you are ready to run the next experiment, 2 years have passed. The Limitless Space Institute does not operate on that timeline. They run a simulation, analyze the results, tweak the parameters, and run it again. The entire cycle takes days, not years. That kind of velocity is what you need when you are exploring a problem space this large. There are thousands of possible warp bubble geometries, tens of thousands of parameter combinations, millions of ways to distribute energy, adjust curvature, and stabilize the field. You cannot explore that space one paper at a time. You need to test configurations in parallel, iterate rapidly, and accumulate data faster than any single research group could manage under traditional academic constraints, and they are accumulating data, terabytes of it. Every simulation produces a snapshot of spacetime geometry at thousands of points in space and time. That data gets stored, indexed, and fed into machine learning models that look for patterns. Configurations that work have features in common. Energy distributions that cluster in certain regions, curvature gradients that fall within specific ranges, The machine learning models are learning what a stable warp bubble looks like, and they are getting better at predicting which configurations will hold together before the full simulation even runs. That feedback loop is accelerating the research. What used to take weeks of computation now takes days. What used to require human intuition to guess the next test is now being handled by algorithms that have seen more warp bubble geometries than any human ever will. The ultimate goal is not just to optimize the Alcubierre drive. It is to find something better, a geometry that nobody has thought of yet. A configuration that does not appear in any published paper because the parameter space is too large to explore by hand. The simulations are searching for that geometry, testing combinations that no human researcher would think to try because they look wrong on paper but might, just might, work when you run the numbers. This is not physics as it has traditionally been practiced. This is physics by brute force. Throw enough computing power at the problem, test enough configurations, accumulate enough data, and eventually the solution emerges. Not because someone had a brilliant insight, because the machine found it. There is a risk in this approach. The risk is that you find a solution that works in simulation but cannot be built in the real world. Computer models are only as good as the physics you put into them. If you are missing something, if there is an effect you did not account for, or a constraint you did not include, the simulation will give you an answer that looks right, but falls apart the moment you try to implement it. That is why the Institute is also working on experimental validation. Not building a warp drive, building the instruments that could detect a warp field if one existed. Refining the interferometer designs, testing new sensor technologies, developing the tools that will let them move from simulation to experiment when the time comes, and the time is coming. Because the simulations are not just theoretical exercises anymore, they are producing geometries that look buildable, energy requirements that look achievable, stability profiles that look controllable. The gap between where we are and where we need to be is still enormous, but it is no longer infinite. And that changes everything, because once the problem stops being impossible and starts being merely very difficult, it becomes an engineering challenge. And engineering challenges, given enough time and resources, get solved. That is what the Limitless Space Institute is betting on. That the data they are generating now, the simulations they are running, the optimizations they are discovering, will be the foundation for the work that comes next. The work that builds the first real warp field, even if it is only a flicker, even if it only lasts a microsecond, even if it is too small to see with the naked eye. Because once you prove the geometry is real, once you show that spacetime can be bent in the way the equations predict, the rest is just scaling up. That is the audacity. Not that they think they can build a warp drive tomorrow, that they refuse to accept that the problem is unsolvable, that they are willing to spend years running simulations, testing geometries, optimizing parameters, and accumulating data on the chance that somewhere in that vast parameter space there is a solution, a configuration of spacetime that does what science fiction has been promising for a century, a way to travel faster than light without breaking the universe. And in late 2024, buried in the data from one of those simulations, they found something, not a complete solution, not a working warp drive, but a crack, a result that should not have been there, a geometry that held together under conditions that every previous model said were impossible. The kind of result that makes you stop, rerun the simulation to make sure it was not a fluke, and then start asking very uncomfortable questions about what you thought you knew. The paper landed in March 2024, not in a press conference, not at a major physics symposium with dramatic reveals and carefully choreographed slide decks, It showed up quietly in Classical and Quantum Gravity, a peer-reviewed journal that publishes maybe a dozen papers a month on topics ranging from gravitational waves to quantum cosmology. The title was dry enough to put most people to sleep before they finished reading it. Physical warp drives with positive energy requirements. No exclamation points, no bold claims about changing the future of space travel. Just another paper in a field that produces hundreds of papers every year, most of which get read by a few dozen specialists and then filed away in the digital archives of academic publishing. Except this one was different, because buried in the math, hidden under layers of tensor calculus and numerical simulations, was a solution to the problem that had kept warp drives locked in the theoretical realm for 30 years. The exotic matter problem. The requirement that had turned every warp drive proposal into a dead end. The need for negative energy density at scales we could not produce and might never be able to produce. The paper, written by a team at Applied Physics, a private research organization based in New York, claimed they had found a way around it, not by discovering a new source of exotic matter, not by proving that negative energy density was easier to create than everyone thought, by eliminating it entirely. The lead author was Jared Fuchs, a physicist who had spent the last several years working on numerical solutions to Einstein's field equations. His co-authors included Christopher Helmerich, a researcher with a background in computational relativity, and Gianni Martia, the CEO of Applied Physics and someone who had been funding warp drive research out of his own pocket since 2021. Martia is not a household name. He is not Elon Musk. He does not have a Twitter following in the millions or a fleet of rockets parked in Texas. He runs a small organization with a specific goal: figure out whether faster-than-light travel is possible, and if it is, build a roadmap for how to get there. The 2024 paper was the first major milestone on that roadmap. The claim, at its core, was simple. You can create a warp drive geometry, a region of spacetime that behaves like an Alcubierre bubble, using only positive energy density, normal matter, the kind we already know how to produce, no exotic matter required, no negative energy, no violations of the quantum inequalities that had shut down every previous attempt to make this work. The geometry still bends spacetime in the way Alcubierre described. Space still contracts in front and expands behind. The ship still rides a wave of curved spacetime from one location to another, but the fuel, the energy distribution that creates and maintains the bubble, is entirely conventional. Positive mass, positive energy density. Stuff we can, in principle, generate and control. That is the breakthrough. Not that they built a warp drive. Not that they demonstrated this in a lab, that they found a mathematical solution, a valid configuration of spacetime that does what a warp drive is supposed to do without requiring the one ingredient that made warp drives impossible. If the paper is correct, and the initial peer reviews suggest it is at least mathematically sound, then the wall just came down. Not completely. Not in a way that lets us build a starship tomorrow, but enough that the conversation shifts. Warp drives stop being a thought experiment and start being an engineering problem. A very hard engineering problem. But engineering problems, no matter how hard, can be solved if you throw enough time and resources at them. The key to understanding how this works is understanding what the paper actually does. It does not invent a new kind of matter. It does not rewrite general relativity. What it does is reframe the problem. Instead of asking, how do we create negative energy density, the authors asked a different question. Can we design a space-time geometry that produces warp effects using only positive energy density? The answer, according to the simulations they ran, is yes. But the geometry has to be very specific, very carefully tuned, And the amount of positive energy you need is still enormous, just not infinite. Here is how it works. In a traditional Alcubierre drive, the warp bubble is created by placing a shell of exotic matter, negative energy density, around the spacecraft. That shell curves spacetime in a specific way. The negative energy pushes spacetime outward, creating the expansion behind the ship and the contraction in front. The ship sits in the middle, in a region of flat spacetime, while the bubble carries it along. The exotic matter is load-bearing. Without it, the geometry collapses, the bubble fails. The warp drive stops being a warp drive and becomes just a region of curved spacetime with no useful properties. The applied physics team started with a different assumption. What if, instead of using exotic matter to push spacetime outward, you used normal matter to pull it inward in a very specific pattern? What if you arranged positive energy density, ordinary mass, in a shell around the spacecraft, but you did it in a way that mimicked the effects of a warp bubble? The idea sounds absurd at first. Normal matter pulls. It does not push. It creates gravitational wells, not gravitational hills. How could you possibly use normal matter to generate the outward pressure, the expansion of spacetime that a warp drive requires? The answer is in the details of the geometry. General relativity does not just care about how much mass you have, it cares about how that mass is distributed and how it moves. A static lump of mass sitting in space curves spacetime one way. A rotating disk of mass curves it differently. A shell of mass moving at relativistic speeds curves it in ways that can produce effects you would not get from a stationary object. The applied physics model takes advantage of this. They designed a shell of positive energy density that is not static. It is dynamic. The mass is distributed in a very specific pattern, and that pattern changes over time in a way that generates the spacetime curvature needed for warp effects. Think of it like this. Imagine you are trying to move a heavy object across a room, but you cannot push it directly. You do not have the strength, so instead you tilt the floor. You create a slope. The object rolls down the slope on its own. You did not push it, you changed the environment around it. The applied physics warp drive does something similar with spacetime. You do not push spacetime outward with exotic matter. You arrange normal matter in a way that tilts spacetime so that the natural flow of geometry does the work for you. The mass is not repelling, the geometry is. The technical term for what they are doing is engineering the stress-energy tensor. That is the mathematical object in general relativity that describes how mass and energy are distributed in spacetime. Change the stress-energy tensor and you change how spacetime curves. Alcubierre's solution used a stress-energy tensor with negative components. Applied physics found a solution that uses only positive components. The curvature they produce is not identical to Alcubierre's, but it is close enough. The spacetime around the ship contracts in front and expands behind. The ship moves. An observer outside the bubble would see it traveling faster than light. An observer inside would experience normal time, normal physics, no exotic effects. There is a catch. There is always a catch. The amount of positive energy you need is absurd. The paper calculates that to create a warp bubble large enough to carry a small spacecraft, something the size of a car, you would need a mass equivalent to roughly 2 Jupiters, 2 gas giants, entire planets' worth of matter compressed into a shell a few meters thick surrounding your ship. That is the energy cost, not infinite, not the mass of the observable universe like Alcubierre's original proposal, but still an amount so large that it might as well be a rounding error away from impossible. 2 Jupiters is more mass than humanity has ever moved in its entire history, more mass than exists in the entire asteroid belt between Mars and Jupiter. More mass than we could conceivably gather, transport or manipulate with any technology currently on the drawing board or even remotely plausible in the next few centuries. And that is just the mass. The paper does not explain how you arrange that mass into the precise geometry required, how you keep it stable, how you move it, how you prevent it from collapsing under its own gravity into a black hole. Those are engineering problems, and they are every bit as hard as the exotic matter problem. Maybe harder, but here is why the paper matters anyway. Because it proves that the energy requirement is not infinite. For 30 years, the assumption was that warp drives required exotic matter, and exotic matter did not exist. End of story. The 2024 paper shows that assumption was wrong. You do not need exotic matter. You need a lot of normal matter, yes, an impractical amount. But impractical is not the same as impossible. Impractical means difficult. It means expensive. It means we do not have the technology yet. All of those problems are solvable in principle. You just need better tools, better energy sources, better ways to manipulate mass at large scales. And we have a history of getting better at those things. The paper also does something else. It introduces a tool. Applied Physics has developed software called Warp Factory, a simulation platform specifically designed to model warp drive geometries and test whether they satisfy the requirements of general relativity. The software is open source. Anyone can download it. Anyone can run their own simulations. Anyone can test new geometries, tweak parameters, and see what happens. This is important because it means the work is no longer confined to a handful of researchers at a single institution. The problem is now open, distributed. Anyone with a computer and enough curiosity can contribute. That kind of open collaboration is how you solve hard problems, not by locking the research behind closed doors, by throwing it open and letting 1,000 people attack it from 1,000 different angles. The simulations the team ran using Warp Factory are the heart of the paper. They modeled dozens of different warp bubble geometries, testing configurations that ranged from variations on Alcubierre's original design to entirely new shapes that no one had tried before. They tested how the energy requirements changed when you adjusted the thickness of the shell, when you changed the rate at which spacetime transitioned from normal to warped, when you added or removed mass from specific regions of the bubble. The goal was to find the configuration that minimized the energy cost while still producing a stable warp field. The result was a geometry that required significantly less energy than Alcubierre's design, not by a small margin, by a factor of 100. 100 times less energy does not mean the problem is solved. Even with that reduction, you are still looking at energy requirements measured in planetary masses, but it does mean the problem is getting smaller. And every time you reduce the energy requirement by a factor of 10 or 100, you open up new possibilities, new ways to approach the engineering, new technologies that might be able to close the gap. A century ago, the energy required to split an atom was considered astronomical. Then we figured out how to do it. Then we figured out how to do it efficiently. Then we built reactors that could generate power by doing it. The trajectory of technology is not linear. It accelerates. Problems that look insurmountable shrink as tools improve. The 2024 paper is betting that the same trajectory applies to warp drives. There is another important detail buried in the results. The warp bubble geometry the team found is stable. That word matters. Stable means the bubble does not collapse the moment you turn it on. It does not tear itself apart. It does not decay into gravitational radiation and vanish in a flash of energy. Stability is one of the hardest requirements to meet in warp drive design because spacetime really does not like being bent into these kinds of shapes. The curvature is extreme, the gradients are sharp, and the equations governing how spacetime responds to stress are unforgiving. Most warp bubble geometries that look good on paper fall apart the moment you try to evolve them forward in time. The applied physics geometry does not. It holds together. That is a big deal. Stability also matters for control. A warp bubble that you cannot steer is useless. The paper does not go into detail about how you would maneuver a ship inside one of these bubbles, but the fact that the geometry is stable suggests that control is at least possible. You could, in principle, adjust the mass distribution in the shell to change the direction of the warp field, strengthen the contraction on one side to turn, reduce the expansion on another to slow down. The precision required would be extreme, but the math says it can be done. That is more than you could say for most warp drive proposals. Most of them do not even get to the point where control is a meaningful question because the geometry collapses before you can test it. The paper also addresses one of the long-standing criticisms of warp drive research, which is that even if you solve the exotic matter problem, you still have the horizon problem. The issue where the ship inside the bubble is causally disconnected from the edges of the warp field and cannot send signals to adjust the geometry. The applied physics design does not completely solve this, but it mitigates it. Because the warp field is generated by a shell of mass surrounding the ship, and that shell is in principle something you can interact with, you are not trying to send a signal through distorted spacetime to reach the front of the bubble. You are adjusting the mass distribution in the shell itself, which is right there with you. The distinction is subtle, but it matters. It means control is not just theoretically possible, it is practically achievable if you can figure out how to manipulate the shell. So how did the physics community react? Cautiously. The paper was peer-reviewed, which means other physicists read it, checked the math, and decided it was worth publishing. That is not a rubber stamp. Classical and Quantum Gravity is a serious journal. If the math was wrong, if the solution violated some fundamental principle of general relativity, the reviewers would have caught it. The fact that the paper was published means the geometry is at least valid. The spacetime curvature they describe is a legitimate solution to Einstein's field equations. That does not mean it is buildable. It does not mean the energy requirements can ever be met. But it means the idea is not nonsense. The reaction from researchers outside applied physics has been mixed. Some are excited. This is the first warp drive model that does not rely on exotic matter, and that alone is a significant step forward. Others are skeptical. Yes, the geometry works, but the energy requirements are still so extreme that calling this a breakthrough feels premature. It is like saying you have solved the problem of traveling to Mars because you figured out how to build a rocket that only requires the entire GDP of Earth to fuel. Technically true, practically useless. The divide between those two camps is where the real debate is happening. Is this a meaningful advance, or is it just trading one impossible problem for a different impossible problem? One name that keeps coming up in discussions of the paper is Alexei Bobrik. He is a physicist who, along with Gianni Martia, published a paper in 2021 that laid some of the groundwork for the 2024 result. The 2021 paper argued that certain classes of warp drives, ones that travel slower than light, could theoretically be built using only positive energy. The key word there is slower than light. Bobrik and Martia were not claiming they had found a way to break the light-speed barrier. They were showing that warp-like effects, space-time geometries that compress and expand in useful ways, could exist without exotic matter as long as you did not push the speed past the speed of light. The 2024 paper builds on that work. It takes the idea further, refining the geometry, optimizing the energy distribution, and demonstrating through simulation that the concept holds together under scrutiny. That distinction, subluminal versus superluminal, is critical. The 2024 paper does not claim to have solved faster-than-light travel. It claims to have solved the exotic matter problem for warp drives that travel at or below the speed of light. That is still useful. A warp drive that could carry a spacecraft at 10% of light speed without requiring exotic matter would cut the travel time to Proxima Centauri from 70,000 years to 40 years. Not fast by human standards, but fast enough that a mission launched today could conceivably arrive within a single human lifetime. That changes the calculus. It makes interstellar travel something you could plan for, rather than something you philosophize about. The paper also does something sneaky with the definition of warp drive. Traditionally, when people talk about warp drives, they mean Alcubierre drives, faster than light, superluminal, the ship inside the bubble moving, from an outside perspective, at 10 times or 100 times the speed of light. But the applied physics model does not do that. It produces warp effects without exceeding light speed. From the perspective of general relativity, that is still a warp drive. Spacetime is being manipulated. The ship is riding a wave of geometry rather than moving through space in the normal sense. But from the perspective of science fiction, and from the perspective of most people who get excited about warp drives, this is not the thing they were hoping for. It is not the USS Enterprise. It is not jumping to warp 9 and crossing the galaxy in an afternoon. It is something slower, more modest, more realistic. And that is either a letdown or a relief, depending on who you ask. For the researchers working on this, realistic is the goal. They are not trying to write science fiction. They are trying to find a path from here to there that does not require rewriting the laws of physics or discovering entirely new forms of matter. Subliminal warp drives, ones that move at a significant fraction of light speed but do not exceed it, are still an enormous leap forward. They are still faster than anything humanity has ever built by orders of magnitude, and they are still, according to this paper, potentially achievable with positive energy. That is the breakthrough, not that we can travel faster than light, that we can bend spacetime without exotic matter. There is one more piece of this worth highlighting. The paper does not just present a single solution. It presents a framework, a method for designing warp drive geometries that satisfy the energy conditions of general relativity without requiring negative energy density. That framework is what makes Warp Factory useful. Other researchers can use the same method to explore different geometries, different mass distributions, different configurations that might reduce the energy requirement even further. The 2024 paper is not the final word. It is the opening move, a proof of concept that shows the approach works. The next step is optimization, testing thousands of variations to see which one gets the energy requirement down to something that looks achievable. Not today, not next decade, but someday. Christopher Helmerich, one of the co-authors, put it this way in an interview shortly after the paper was published. The design still requires a considerable amount of energy, but it shows that warp effects can be achieved without exotic forms of matter. That is the exact right level of caution. Yes, this is progress. No, it is not a working warp drive. It is a data point, a proof that the problem is not as impossible as it looked. And in a field where progress is measured in decades, a data point like that matters. What does this mean for the future? It means warp drive research just got a second wind. For 30 years, the conversation was stuck. Alcubierre proved the geometry was possible, and physics proved the geometry was impractical. No one knew how to move past that. The 2024 paper moves past it. Not by solving every problem, by removing one of the biggest barriers. The exotic matter requirement is gone. Replaced with a different requirement, yes, a difficult requirement, but one that is in principle achievable if we ever figure out how to manipulate energy at planetary scales. That is a long way off, centuries maybe, but it is not infinite, and that is the difference between a dead end and a very long road. It also means that the people who have been working on this in private labs and academic side projects were not wasting their time. The simulations Harold White ran at NASA, the models the Limitless Space Institute has been testing, the papers that researchers like Bobrick and Martier published arguing that warp drives might be possible without exotic matter, all of that work just became more relevant. Because now there is a concrete example, a published, peer-reviewed solution that shows it can be done. Not easily, not cheaply, but done. And that brings us to the next question. If warp drives are theoretically possible without exotic matter, what else is possible? Wormholes, the hypothetical tunnels through spacetime that connect distant points, also require exotic matter in every model we have. Do they still? Or is there a way to build a wormhole using only positive energy, the same way applied physics built a warp bubble? What about traversable wormholes, the kind you could actually send a ship through without it being crushed by tidal forces or incinerated by radiation? What about communication across interstellar distances, faster than light signals that do not require moving a physical object? If spacetime can be bent in ways we did not think were possible, what other doors just opened? Those are the questions that come next. Because the 2024 paper did not just solve one problem. It cracked open an entire field of possibilities that most physicists had written off as permanently closed. The problem with solving one impossible thing is that it immediately forces you to look at all the other impossible things you had written off. For 30 years, warp drives lived in the same mental category as perpetual motion machines and faster-than-light communication. Theoretically interesting, mathematically consistent, and utterly impractical. The exotic matter requirement was the wall, the barrier that kept these ideas locked in the realm of thought experiments. And now, if the 2024 paper is correct, that wall just developed a crack. Not a hole you can walk through, not yet, but a crack, and cracks have a way of spreading. Warp drives were never the only idea on the table, they were just the most famous. The concept that made it into science fiction, into television shows, into the cultural imagination. But there is another geometry hiding in the equations of general relativity that is, in some ways, even stranger, even more useful, and even more dependent on the one ingredient we could not produce: wormholes, tunnels through spacetime. Shortcuts that connect two distant points in the universe by bending the fabric of reality itself into a bridge. Einstein and Nathan Rosen described the basic idea in 1935, decades before anyone thought seriously about warp drives. The technical term is an Einstein-Rosen bridge, though almost no one calls it that anymore. The word wormhole, coined by physicist John Wheeler in the 1950s, stuck because it is a perfect metaphor. Imagine an apple. A worm on the surface of the apple wants to get to the opposite side. It could crawl across the surface, covering the full distance, or it could burrow straight through the middle, cutting the journey to a fraction of the original length. The worm is not moving faster, the path is just shorter. That is what a wormhole does to spacetime. It does not let you travel faster than light through normal space. It gives you a path where the distance itself is compressed. The math works. Einstein's field equations allow for solutions where spacetime folds back on itself, creating a tunnel. One end of the tunnel sits in one location, the other end sits somewhere else, light years away, across the galaxy. On the other side of the universe, the distance through the tunnel could be a few meters. Step into one end, walk forward, step out the other end, and you have crossed an interstellar void without ever exceeding the speed of light locally. From your perspective, you took a short walk. From the perspective of someone watching from outside, you just traveled faster than light because you covered a distance that light, moving through normal space, would take years to cross. But you did not break any rules. You found a shortcut. Here is the problem. The same problem that has plagued wormholes since the moment physicists realized they were possible. The tunnel collapses immediately. The moment you try to open a wormhole, the geometry becomes unstable. The throat, the narrow part of the tunnel connecting the two ends, pinches shut. Spacetime snaps back to its normal configuration. The bridge disappears, and anything that was inside the tunnel when it collapsed gets crushed out of existence by forces that would make a black hole look gentle. The throat of a wormhole is not a stable structure. It wants to close. Gravity pulls it inward. The curvature of space-time around the opening pulls it tighter, and unless you do something to hold it open, it will collapse faster than light can travel through it. Which means even a photon, the fastest thing in the universe, cannot make it from one end to the other before the tunnel ceases to exist. The only way to keep a wormhole open is to thread it with something that pushes outward instead of pulling inward, something that exerts negative pressure, something with negative energy density. Exotic matter, the exact same substance that warp drives require, the substance that might not exist, the substance that quantum field theory says you cannot produce in useful quantities. Without exotic matter, wormholes collapse. With it, they become traversable, stable, usable, a permanent bridge between 2 points in space that you could travel through as casually as walking through a doorway. For decades, this kept wormholes in the same impossible category as warp drives. The geometry was allowed, the physics was sound, but the practical requirement, the need for exotic matter, was a showstopper. And because wormholes and warp drives both relied on the same unattainable ingredient, most physicists treated them as a package deal. Solve one, and you might solve the other. Fail to solve one, and both remain fantasies. The 2024 warp drive paper changed that calculation. Because if you can create a warp bubble using only positive energy density, using normal matter arranged in a very specific geometry, then the question becomes whether you can do the same thing for a wormhole. Can you stabilize the throat of a wormhole, keep it from collapsing, using only positive energy? No one has published a paper claiming to have done it yet. But the fact that it is now a question worth asking, rather than a question with an obvious no answer, is a shift, a significant one. The connection between warp drives and wormholes runs deeper than just the exotic matter requirement. Both are solutions to Einstein's field equations. Both involve extreme curvature of spacetime. Both allow for effective, faster-than-light travel, without technically violating the light speed limit. And both have the same basic problem, which is that the geometries required are so specific, so finely tuned, that even a small error in the configuration causes the whole thing to fall apart. A warp bubble that is slightly asymmetric does not just perform poorly, it collapses. A wormhole throat that is not perfectly stabilized does not just narrow, it pinches off. The tolerances are extreme, and that makes both concepts extraordinarily difficult to engineer, even if you solve the energy problem. There is another issue with wormholes that does not get as much attention, but is every bit as troubling: causality. If you can travel through a wormhole from point A to point B faster than light could make the journey through normal space, then from the perspective of certain observers you are moving backward in time. Not literally, you are not seeing events reverse, but the ordering of events, the sequence of cause and effect, starts to look wrong. Relativity says that different observers moving at different speeds, will disagree about the timing of events. That is fine, that is normal. Special relativity has been dealing with that since 1905. But if you introduce a shortcut, a path through spacetime that lets you cover a distance faster than light would through normal space, then some observers will see you arrive at your destination before you left. And if you can do that, then in principle, you could use the wormhole to send a signal to yourself in the past. Which creates a paradox. The kind of paradox that breaks causality. The kind that general relativity does not like. Physicists have spent a lot of time arguing about whether this is a real problem or just a feature of the math that looks wrong but does not actually cause contradictions. The consensus, to the extent there is one, is that if wormholes are possible, then the universe probably enforces some kind of protection mechanism that prevents you from using them to violate causality. Maybe the energy requirements become infinite the moment you try to send something backward in time. Maybe quantum effects destroy the wormhole before the paradox can occur. Maybe there is a rule we have not discovered yet that forbids certain kinds of shortcuts. No one knows, but the fact that general relativity allows geometries that seem to permit time-travel paradoxes has made a lot of physicists very uncomfortable. And that discomfort is part of the reason wormholes have not been taken as seriously as they might otherwise be. Now assume for a moment that the exotic matter problem is solved. Assume that the techniques applied physics used to create a warp bubble with positive energy can be extended to wormholes. Assume you can thread the throat of a wormhole with normal matter arranged in a way that exerts the outward pressure needed to keep it stable. What do you get? A tunnel. A permanent, traversable connection between 2 points in space. Not a vehicle, not a ship. A piece of infrastructure, a bridge. Once you build it, it stays there. Anyone can use it. You step in one end, step out the other, and the journey is instantaneous from your perspective. No engines, no fuel, no need to accelerate or decelerate. You are just somewhere else. The implications are staggering. A single wormhole connecting Earth to Alpha Centauri would make interstellar travel trivial. Not fast in the sense of traveling quickly, instantaneous. You could walk to another star the way you walk to another room, build a dozen wormholes and you have a network, a transportation system connecting distant stars as if they were neighboring cities. The distances do not matter anymore. The galaxy stops being a vast emptiness that takes lifetimes to cross and starts being a place you can navigate as easily as a highway system. You do not need faster ships. You do not need better engines. You need one piece of infrastructure per destination, and the problem is solved. That is the dream, the idea that has been sitting in science fiction for nearly a century. Star Trek had wormholes. Stargate was built entirely around the concept. The math says they are possible. The engineering says they are impossible. And the 2024 warp drive paper suggests the engineering might be wrong, not solved, not easy. But maybe, possibly, not as impossible as we thought. And if that is true, then the next few decades of research are not going to be about building faster rockets. They are going to be about figuring out whether we can bend space-time into stable, usable geometries that let us skip the travel part entirely. There is one more angle to this that almost no one is talking about yet, but it is going to become important very quickly. If warp drives and wormholes are possible, even in principle, then they might already exist. Not here, not built by us, but somewhere. Built by someone else, an advanced civilization that figured this out 1,000 years ago or 1,000,000 years ago and has been using warp drives or wormholes or both as part of their infrastructure ever since. And if that is the case, then there should be evidence, signatures, observable effects that we could detect with telescopes or gravitational wave detectors or other instruments if we knew what to look for. This is not wild speculation. This is a serious line of research that has been gaining traction over the last few years. The field is called technosignatures, and it is focused on finding evidence of advanced technology in the cosmos. Not radio signals, not alien spacecraft buzzing past Earth. Signatures in the data, patterns that do not fit natural explanations. Anomalies that only make sense if someone somewhere is doing something we have not figured out how to do yet. Warp drives and wormholes are high on the list of things that might leave detectable signatures. Because bending spacetime is not a quiet process, it produces effects, radiation, gravitational waves, distortions in the light from background stars. If someone is running a warp drive within a few million light-years of Earth, and if that warp drive behaves the way our models predict, we should be able to see it. The 2024 paper on warp drive signatures explored this directly. The authors modeled what would happen if a warp bubble traveling at 10% of light speed suddenly collapsed. The geometry destabilizes. The space-time curvature that was holding the bubble together snaps back to normal, and that snap releases energy, a lot of energy, in the form of gravitational waves, ripples in space-time itself, radiating outward at the speed of light. The frequency of those waves depends on the size of the bubble and the speed it was traveling. For a bubble large enough to carry a spacecraft, collapsing at 10% of light speed, the gravitational wave signal would peak around 300 kHz. That is much higher than the frequencies LIGO detects. LIGO is tuned to listen for black hole mergers and neutron star collisions, which produce gravitational waves in the range of tens to thousands of hertz. 300 kHz is off the chart, way above what current detectors can measure. But that does not mean the signal is undetectable. It just means we need different instruments. Gravitational wave astronomy is still in its infancy. LIGO was the first detector to confirm gravitational waves in 2015. Less than a decade later, we have a handful of detectors online and plans for more. Future instruments will cover higher frequencies, different bands, and if someone builds a detector capable of measuring gravitational waves in the hundreds of kilohertz range, and if that detector picks up a signal that matches the profile of a collapsing warp bubble, then we will have found something. Not proof of alien life, not direct contact, but evidence that someone, somewhere, is bending space-time in ways that nature does not. The distance matters. The 2024 study estimated that a collapsing warp drive would be detectable out to about 1 megaparsec. That is roughly 3.26 million light-years. For context, the Andromeda Galaxy, the nearest large galaxy to the Milky Way, sits about 2.5 million light-years away. So we are talking about a detection range that covers our local group of galaxies, not the entire universe. Not even a significant fraction of it, but enough to matter. If advanced civilizations exist within that bubble, and if they are using warp drives, and if those warp drives occasionally fail or shut down in ways that produce gravitational wave bursts, we could detect them, not with current technology, but with instruments that are plausible to build in the next few decades. The signature would not be subtle. A collapsing warp bubble releases energy on a scale comparable to certain types of supernova events. The gravitational wave burst would be brief, a few milliseconds, but intense, detectable across millions of light-years if your instruments are tuned to the right frequency. The challenge is distinguishing that signal from natural sources. The universe is full of things that produce gravitational waves. Merging black holes, colliding neutron stars, supernovae. Anything that involves large amounts of mass accelerating in extreme gravitational fields. A warp bubble collapse would have a specific signature, a specific frequency profile, a specific duration. But proving that the signal you detected came from an artificial source rather than some exotic natural phenomenon no one has thought of yet is hard. You need multiple detections. You need to rule out other explanations. You need data, lots of it. This is where the connection to SETI becomes relevant. SETI, the search for extraterrestrial intelligence, has spent decades scanning the skies for radio signals from alien civilizations. The assumption has always been that if aliens want to communicate, they will broadcast, send out a signal, make themselves known. That assumption has not panned out. We have found nothing. No confirmed alien signals, no smoking gun, and after 60 years of searching, some researchers are starting to wonder whether we are looking for the wrong thing. Maybe advanced civilizations do not broadcast, maybe they do not want to be found, or maybe they communicate using methods we have not thought to look for. Gravitational waves, neutrino beams, modulated gamma-ray bursts, or signatures left behind by their technology, waste heat from Dyson spheres, the glow of antimatter engines, the gravitational wave chirp of a collapsing warp drive. The shift from searching for signals to searching for signatures is subtle but important. Signals are intentional. Someone has to decide to broadcast. Signatures are incidental, byproducts of doing something else. If you are running a warp drive, you are not trying to send a message to distant observers. You are just trying to get from one star to another. But the act of doing that leaves a mark, a ripple in spacetime, a burst of radiation, an anomaly in the data. And if we build instruments sensitive enough to detect those marks, we do not need aliens to cooperate. We just need them to exist and to be using technology that bends the universe in detectable ways. Wormholes would leave different signatures. A stable wormhole, one that is being held open by some kind of exotic or engineered matter, would distort the light from stars behind it. Gravitational lensing, the same effect we see around black holes and galaxy clusters. Light bends as it passes through curved spacetime, and the pattern of that bending tells you about the mass distribution causing it. A wormhole mouth would produce a very specific lensing pattern, one that does not match a star, a planet, or a black hole. If you saw that pattern in telescope data, and if you could rule out other explanations, you would have found something, not proof of aliens, but proof that spacetime in that region is curved in a way that should not happen naturally. The problem is that space is big. The number of stars, the number of regions you would have to survey to have a reasonable chance of spotting something like this is enormous. And we do not have telescopes capable of surveying the entire sky at the resolution needed to detect subtle lensing anomalies around distant stars. The James Webb Space Telescope can do a lot of things, but it cannot scan the whole galaxy looking for wormholes. Its field of view is too narrow. Its observation time is too limited. What we need is a dedicated survey, a telescope or a network of telescopes designed to look for anomalies, not just wormholes, anything that does not fit, gravitational lensing that is too strong or too weak, light curves from stars that dim in ways that do not match planets or dust clouds, spectral signatures that do not correspond to any known element or molecule. The broader you search, the more likely you are to find something strange. And once you find something strange, you can point more sensitive instruments at it and figure out what it actually is. This kind of work is already happening at the edges. The Breakthrough Listen project, funded by Yuri Milner, is scanning millions of stars for radio and optical signals, not just narrow-band signals that look like broadcasts. Anything unusual. The Vera Rubin Observatory, set to begin operations soon, will survey the entire southern sky every few nights, generating a massive dataset of everything that changes or moves: supernovae, asteroids, variable stars, and maybe, if we are lucky, something that does not fit any of those categories, something that looks artificial, or at least looks like it should not be there. The intersection between faster-than-light research and techno-signatures is just beginning to be explored. For a long time, these were separate fields. Warp drives and wormholes lived in the realm of theoretical physics. And techno-signatures lived in the realm of observational astronomy. They did not talk to each other much because there was no overlap. Warp drives were impossible, so there was no point looking for them. But if the 2024 paper is right, if warp drives are not impossible, just very difficult, then the calculus changes. Suddenly it becomes reasonable to ask whether anyone else has figured this out. And if they have, what would we see? The answer is we do not know yet. The models are too new. The simulations are still being refined. The detection methods are still being developed, but the conversation is happening. Papers are being written, conferences are being planned, and funding, the kind of funding that lets you build instruments and run surveys, is starting to trickle in. Not a flood, not anywhere close to what gets spent on particle accelerators or space telescopes, but enough to matter. Enough that in 10 or 20 years we might actually have the tools to search for warp drive signatures or wormhole lensing or other exotic phenomena that could only exist if someone is out there doing things we have not figured out how to do. One of the researchers leading this effort is Geraint Lewis, an astrophysicist who has spent years working on gravitational lensing and large-scale structure in the universe. He has been vocal about the need to take techno-signatures seriously, not because he believes aliens are everywhere, but because the cost of not looking is potentially enormous. If advanced civilizations exist, and if they are using technology that leaves detectable signatures, and if we fail to notice because we were not looking in the right places or at the right frequencies, we will have missed one of the most important discoveries in human history. The risk of looking and finding nothing is low. A few wasted telescope hours, a few papers that do not pan out. The risk of not looking and missing something is infinite. We do not get a second chance at first contact. If the evidence is there and we ignore it, we might not get another opportunity for centuries. There is also the possibility that we find something and do not recognize it. That the signature is there sitting in the data and we mistake it for noise or a glitch or some natural phenomenon we have not catalogued yet. That has happened before. Pulsars, the rapidly spinning neutron stars that emit beams of radio waves, were first detected in 1967. The signal was so regular, so precise, that the researchers who found it briefly considered whether it might be artificial. They even nicknamed the source LGM1, Little Green Men 1. It turned out to be natural, a neutron star rotating 30 times per second. But the fact that they considered an artificial explanation even for a moment shows how hard it is to distinguish between the strange and the artificial when you are working at the edge of what is known. The same caution applies to warp drive signatures. If we detect a gravitational wave burst at 300 kHz, and if that burst matches the profile predicted by the collapsing warp bubble model, the first instinct will be to look for a natural explanation. Maybe it is a new kind of stellar explosion. Maybe it is a previously unknown interaction between black holes. Maybe it is an error in the data processing pipeline. You do not jump straight to aliens built a warp drive and it broke. You exhaust every other possibility first, and only when you have ruled out everything else, when the data refuses to fit any natural model, do you start considering the artificial explanation, That process takes time, years, maybe decades. And even then, you are not proving the signal is artificial. You are just saying it does not fit anything we know about. The challenge is compounded by the fact that we have exactly one example of a technological civilization, us. We have no idea what other civilizations, if they exist, would prioritize, what technologies they would develop, what signatures their infrastructure would leave. We assume they would use radio because we use radio. We assume they would build megastructures because we think about building megastructures. We assume they would leave detectable waste heat because our technology generates waste heat. But all of those assumptions are based on a sample size of 1. If alien civilizations are out there, and if they are advanced enough to have solved faster than light travel, their technology might look nothing like ours. The signatures might be completely different. We might be looking for the wrong things in the wrong places at the wrong times, and we would never know. That uncertainty is part of why this work matters, because even if we do not find warp drives or wormholes, even if the search comes up empty, the act of looking forces us to think about what advanced technology might look like from a distance. It forces us to refine our models, to develop better instruments, to ask questions we would not have thought to ask otherwise. And those questions, those tools, those models have applications beyond just searching for aliens. Gravitational wave astronomy is useful for studying black holes and neutron stars. High-resolution sky surveys are useful for tracking asteroids and monitoring supernovae. The techniques we develop to search for artificial phenomena will also make us better at understanding natural phenomena. That is how science works. You aim for one goal and end up discovering 10 other things along the way. So here is where we are. Warp drives might not require exotic matter. Wormholes might be stabilized using similar techniques. If either of those technologies exist anywhere in the universe, they should leave signatures, gravitational waves, lensing anomalies, radiation bursts, and we are just now beginning to build the instruments that could detect those signatures, not today, not next year, but soon, within a generation. The next few decades are going to see an explosion in our ability to observe the universe at frequencies, resolutions, and sensitivities that were unimaginable 20 years ago. And somewhere in that flood of data, if we are lucky, there might be a signal that does not fit, an anomaly that refuses to be explained by natural processes, a hint that someone, somewhere, figured out how to bend spacetime and went ahead and did it. That possibility, remote as it is, changes the stakes, because if faster-than-light travel is real, if it is achievable, then the universe is not as empty as it looks. The distances are not as insurmountable as they seem. And the future of humanity is not confined to this single star system, waiting thousands of years for generation ships to crawl to the nearest neighboring worlds. The future could be faster, stranger, more connected than we ever imagined, not because we broke the laws of physics, because we finally learned to read them correctly. The road ahead is not clear. That is the first thing worth saying plainly before we start talking about timelines and engineering challenges and the grand future of humanity spreading across the stars. The road is not clear because we are standing at the very beginning of it, squinting into the distance, trying to make out shapes that might be milestones or might just be shadows. The 2024 breakthrough, the applied physics paper showing that you can create a warp bubble geometry without exotic matter, is not a map, it is a signpost. It tells us we are facing the right direction. It does not tell us how far we have to walk or what obstacles are waiting around the next bend. Start with the timeline because that is the question everyone asks first. How long until we build a warp drive? The honest answer is we do not know. The optimistic answer, the one that assumes every problem we encounter has a solution and every solution is found faster than expected, is still measured in decades. Plural, not 5 years, not 10. The kind of decades where you launch a research program today and the people who see it succeed are your grandchildren. That is the optimistic answer. The realistic answer is longer. Centuries, maybe. The pessimistic answer is never. That we hit a wall we cannot engineer around. That the energy requirements stay impossibly high. That the geometry works on paper and fails in practice for reasons we do not discover until we try to build the thing and watch it collapse. All three answers are on the table. And which one turns out to be correct depends entirely on what happens in the next phase of research. That next phase is not building a warp drive. It is building the tools that let you test whether a warp drive is even possible at scales larger than a computer simulation. The White-Jude warp field interferometer that Harold White built at NASA was the first attempt at this. A device sensitive enough to detect tiny distortions in spacetime if those distortions matched the signature of a warp field. The results were inconclusive. The instrument was at the edge of its sensitivity. The signal, if it was there, was buried in noise. What comes next is a better version of that instrument, more sensitive, more stable, capable of ruling out false positives and confirming whether the geometries the simulations predict can actually be created in a lab, not at spacecraft scale, at the scale of a laser beam passing through a carefully engineered region of space where you have done something, anything, that bends space-time in the right way. Detect that, measure it, confirm it, and you have crossed the line from theoretical to experimental. You have proven the concept works in reality, not just in equations. Building that instrument is hard. Detecting space-time curvature at the scales we are talking about requires precision that makes gravitational wave detectors look crude. LIGO, the detector that confirmed gravitational waves in 2015, measures distortions in spacetime on the order of 1/10,000th the width of a proton. The kind of distortion a warp field would produce in a lab setting, if you could produce one at all, would be smaller, orders of magnitude smaller. You are looking for a ripple in the fabric of reality so faint that every other source of noise, every vibration in the building, every thermal fluctuation in the equipment, every stray electromagnetic field drowns it out. The engineering required to build a detector that can see through all that noise and pull out a clean signal is at the absolute edge of what current technology can do, maybe past that edge. But it is not impossible. It is just expensive, time-consuming, and requires the kind of focus that does not happen unless someone with money decides this is worth funding. The funding question is where things get messy. Governments fund science when there is a clear return, national security, economic advantage, prestige. Warp drive research does not fit neatly into any of those categories yet. It is too far out, too speculative, too easy for a congressional committee to look at and decide the money is better spent on something with a more immediate payoff. Private funding is unpredictable. You get bursts of interest when someone wealthy gets excited about the idea, and then the money dries up when they move on to the next thing. The Limitless Space Institute operates on a shoestring budget. Applied physics is slightly better funded but still small compared to the kind of resources you would need to build a serious experimental program. What changes that is results. Publish a paper showing that you detected a warp field in a lab, even a microscopic one, and the funding situation shifts overnight. Suddenly it is not speculative, it is real, and real gets money. Assume the detector gets built. Assume the experiments run. Assume the results come back positive. You have confirmed that spacetime can be bent into a warp bubble geometry using only positive energy density. What happens next is optimization. You take the geometry that worked in the lab and start scaling it up, not to spacecraft size, not yet, to something larger than a laser beam but smaller than a marble. You test whether the bubble remains stable as you increase the size. You measure how much energy it takes to create and maintain. You explore whether you can control it, steer it, accelerate it, decelerate it. Every one of those steps is a separate research program. Every one of them takes years, and every one of them has a chance of failing in ways that send you back to the drawing board. The energy problem does not go away just because you proved the geometry works. The applied physics paper showed that you can, in principle, create a warp bubble with positive energy, but the amount of energy required is still absurd. 2 Jupiters' worth of mass converted into energy and arranged in a shell around your spacecraft. That is not a number you can engineer around by building a better battery. That is a number that requires rethinking how we generate and store energy at scales we have never approached. Fusion power, if we ever get it working reliably, might close part of that gap. Antimatter, if we figure out how to produce it in large quantities and store it without it annihilating everything it touches, might close more. But even with those advances, the gap between what we can do and what a warp drive requires is enormous. You are not talking about incremental improvements. You are talking about breakthroughs, multiple breakthroughs, in fields that are themselves still experimental. Fusion has been 10 years away for the last 60 years. That is not a joke, that is the timeline. Every decade, researchers announce they are getting closer, and every decade, the practical application remains just out of reach. The latest results from the National Ignition Facility, where they achieved net energy gain from a fusion reaction for the first time in 2022, are encouraging. But net energy gain in a controlled lab setting is not the same as net energy gain in a reactor that can power a city, let alone a reactor that can generate the energy needed to bend spacetime. The jump from proof of concept to practical application is where most technologies stall. Fusion is no exception. If it takes another 50 years to get fusion power online, and another 50 years to scale it up to the point where you can use it for something like a warp drive, you are looking at a timeline that stretches into the 22nd century. That is not pessimism. That is just how long it takes to move from the lab to the world when the engineering challenges are this hard. Antimatter is even worse. We produce antimatter today. Particle accelerators create it in tiny quantities every time they smash protons together at high energies. The problem is that producing even a single gram of antimatter would require more energy than the entire planet consumes in a year, and storing it is a nightmare. Antimatter annihilates the moment it touches normal matter. You have to keep it suspended in a magnetic trap, isolated from everything, and even then, the traps are not perfect. A single failure, a single fluctuation in the magnetic field, and the antimatter touches the wall of the container and explodes. The energy density of antimatter is unmatched. 1 gram of antimatter reacting with 1 gram of normal matter releases as much energy as a small nuclear bomb. But if you cannot produce it cheaply and store it safely, it is useless. The engineering required to make antimatter a practical energy source is so far beyond what we can currently do that most researchers do not even bother trying. They just note that it exists, acknowledge that it would be useful if we could figure it out, and move on to other ideas. The materials problem is just as hard. A warp bubble, even one that uses positive energy, is still a region of extreme spacetime curvature. The stresses on anything inside or near that bubble are going to be enormous. You need materials that can withstand those stresses without deforming, fracturing, or vaporizing. We do not have those materials. The strongest materials we have today, things like carbon nanotubes or graphene, are strong by human standards. They are not strong enough to handle the kind of forces you encounter when you start bending spacetime. The solution is probably not a material we dig out of the ground or synthesize in a lab using current techniques. The solution is probably something we engineer at the atomic level. Custom-designed structures where every atom is placed exactly where it needs to be to maximize strength and minimize weight. That kind of engineering exists today in very limited forms. Nanotechnology labs can build tiny structures, a few nanometers across, with that kind of precision. Scaling that up to the size of a spacecraft is a problem no one has solved. And until someone does, the materials question remains a hard stop. There is also the control problem. A warp bubble that you cannot steer is a missile. You point it at a target, turn it on, and hope it goes where you aimed. That might be acceptable for an unmanned probe. It is not acceptable for a crewed mission. You need real-time feedback, sensors that can measure the space-time curvature around the bubble with enough precision to detect errors before they cascade. Computers fast enough to recalculate the geometry and adjust the energy distribution in milliseconds. Control systems that can manipulate the shell of energy surrounding the ship without destabilizing the entire structure. Every one of those requirements pushes the limits of what current technology can do. Sensors that measure space-time curvature exist. Gravitational wave detectors do this. But they are enormous, fragile, and slow. You cannot fit one inside a spacecraft. You need something smaller, faster, and tougher. You need computers that can solve Einstein's field equations in real time, not in hours. And you need actuators, whatever those end up being, that can move energy around inside the warp bubble faster than the bubble itself is moving. None of that exists yet. None of it is impossible, but all of it is hard. Assume we solve those problems. Assume we build the detector, confirm the geometry, optimize the energy requirements, develop the materials, and figure out the control systems. You still do not have a warp drive. You have a prototype, a test article, something that might work once under ideal conditions if everything goes right. The next step is testing, and testing a warp drive is dangerous in ways that are hard to overstate. If the bubble collapses while the ship is inside, the space-time curvature snaps back to normal in a fraction of a second. Anything caught in that transition gets torn apart by tidal forces that would make a black hole look gentle. If the energy distribution shifts unexpectedly, the bubble could destabilize and dump all that energy into the surrounding space in a burst of radiation intense enough to sterilize everything within a few kilometers. If the geometry is even slightly wrong, the ship could end up somewhere other than where you aimed. Somewhere very far away, with no way to get back. The first tests are not going to involve people. They are going to involve drones, small unmanned spacecraft loaded with sensors, transmitting data back in real time and designed to be expendable. You send one through a warp bubble. You measure what happens. If it survives, you send another one. You repeat the test 100 times, 1,000 times, until you are confident the system is stable and predictable. Then you start testing larger payloads, heavier spacecraft, longer distances, higher speeds. Every step is incremental. Every step takes years, and at any point something could go wrong in a way that sends you back to the beginning. That is how experimental engineering works. You do not build the final version first. You build the version that fails in predictable ways so you can learn what needs to change. Now assume we get through all of that. Assume we build a working warp drive, a spacecraft capable of traveling faster than light, or at least at a significant fraction of light speed, by bending spacetime around itself. Who decides where it goes? Who gets to use it? Who pays for it? Those are not engineering questions. Those are political questions. And political questions are harder than engineering questions because there is no equation that tells you the right answer. There is just negotiation, compromise, and the uncomfortable reality that anything capable of crossing interstellar distances in a human lifetime is also capable of being weaponized in ways that make nuclear missiles look quaint. A warp drive is, by definition, a tool for moving enormous amounts of energy across vast distances very quickly. That makes it useful for exploration. It also makes it useful for other things. Things that international treaties and security councils are going to spend years arguing about before the first test flight ever happens. The Outer Space Treaty of 1967 says that space is the province of all mankind and that no nation can claim sovereignty over celestial bodies. It also says that weapons of mass destruction cannot be placed in orbit or on the moon or anywhere else in space. Does a warp drive count as a weapon of mass destruction? It does not carry a warhead, but it carries energy, a lot of energy. Enough that if you pointed it at a planet and let the bubble collapse at the wrong moment, you could do damage on a scale that would make conventional weapons irrelevant. The treaty does not cover that because no one in 1967 imagined it would ever be possible. Updating international law to account for technologies that do not exist yet is not something humanity is good at. We wait until the technology is real, until someone has built it and demonstrated it, and then we scramble to write rules. By that point, the rules are always reactive, always playing catch-up. The smarter approach would be to start the conversation now, before the first prototype, before the first test flight. Lay out the principles, decide who gets access, decide what uses are allowed and what uses are banned. Decide how to enforce those bans when the technology is controlled by private companies or rogue states or anyone else who does not feel like following the rules. That conversation is not happening yet. It needs to. There is also the resource question. If faster-than-light travel becomes possible, even at the level of sending small probes to nearby stars, the economic implications are staggering. The asteroid belt between Mars and Jupiter contains more metal than humanity has mined in its entire history. The moons of Jupiter and Saturn contain more water than all the oceans on Earth. The outer solar system is full of resources we could use if we could get to them quickly and bring them back. Warp drive does not just open the door to other stars. It opens the door to our own solar system in ways that are not currently practical. A mission to Jupiter takes years. A warp-capable probe could make the trip in weeks or days. That changes the economics of space exploration. It makes things viable that are currently too expensive or too slow to consider. Beyond the solar system, the resource picture gets even stranger. If you can reach another star system, and if that star system has planets, and if those planets have materials we do not have here, you have just unlocked access to an effectively infinite supply of everything. Rare earth elements, heavy metals, exotic compounds that only form under conditions we cannot replicate in a lab. The universe is not short on resources, it is short on accessibility. Warp drive solves the accessibility problem. And the moment you solve that, the entire economy of Earth changes, not gradually, overnight. Because the scarcity that drives prices, that makes some materials valuable and others cheap, stops being real. Platinum is expensive because it is rare, but it is only rare on Earth. In the asteroid belt, there are rocks made almost entirely of platinum drifting around doing nothing. Go get one, bring it back, crash the platinum market, repeat for every other rare material. The economic disruption would be comparable to the Industrial Revolution, except compressed into a few decades instead of a few centuries. That disruption comes with winners and losers. The people who control access to warp technology, who own the ships or the infrastructure or the legal rights, become wealthier than anyone in history. The people who depend on Earth-based industries that suddenly have to compete with asteroid mining or off-world manufacturing lose. Entire economies collapse. Entire regions built around extracting or refining materials that are no longer scarce face unemployment on a scale that makes the decline of coal mining look like a minor adjustment. Managing that transition is a political and social challenge every bit as hard as the engineering challenge of building the warp drive in the first place. And it is a challenge we are not talking about yet because the technology still feels too far away to matter. It is not. If the optimistic timeline is right, if we confirm the geometry works and start building prototypes in the next few decades, the economic shockwaves hit within a human lifetime. That is soon enough that we should be planning for it now. Then there is the ethical question of what we do when we get to another star. Assume we send a probe to Proxima Centauri. It arrives. It sends back data. The data shows planets. One of them is in the habitable zone, liquid water, an atmosphere, maybe even signs of life, microbial life. Nothing intelligent. Just bacteria or algae or something simple. Do we go there? Do we land? Do we take samples? Do we leave it alone? The answer depends on who you ask. Some scientists would say we have an obligation to study it. That understanding life in another environment, life that evolved completely independently from Earth, is one of the most important discoveries we could make. Others would say we have an obligation to leave it alone. That contaminating another biosphere with Earth organisms or contaminating Earth with alien organisms when we bring samples back is a risk we cannot justify. Both arguments are reasonable, both are rooted in values that are hard to argue against. And there is no neutral arbiter who can settle the debate. It is a choice. And choices, especially ones with consequences this large, do not get easier just because we have better technology. The same question applies to colonization. If we find a planet that could support human life, do we go there and settle it? Do we terraform it? Change its atmosphere and climate to make it more Earth-like, even if that means destroying whatever ecosystems already exist? Do we build habitats on planets that are completely lifeless and avoid interfering with the ones that are not? Do we enforce those rules internationally, or do we let individual nations or corporations decide for themselves? Every one of those questions has been explored in science fiction. Very few of them have been explored in policy discussions or international law. And the answers we come up with now, before we have the technology to make them real, are going to shape what humanity does for the next 1,000 years. We do not get to revisit those decisions. Once we start spreading to other stars, the trajectory is set. The choices we make today echo forward through centuries. There is also the possibility that we are not the first. That someone else, some other civilization, figured this out before we did and has been using warp drives or wormholes or some other method of faster-than-light travel for thousands or millions of years. If that is true, then the moment we turn on our first warp drive, we announce ourselves. We step onto a stage that we did not know existed, and we have no idea who else is on that stage or how they are going to react. That possibility, remote as it sounds, is taken seriously by a growing number of researchers, not because they believe aliens are likely, because the consequences of being wrong are so extreme that even a small probability is worth considering. If advanced civilizations exist, and if they are monitoring the galaxy for signs of emerging technologies, a warp drive is exactly the kind of thing that would get their attention. A burst of gravitational waves, a distortion in spacetime, a signature that does not match anything natural. You light that beacon and you are visible. And visibility comes with risks we cannot predict because we have no idea what we are making ourselves visible to. The optimistic scenario is that other civilizations are out there, they are friendly, and they have been waiting for us to reach the point where we can join them. The pessimistic scenario is that they are out there, they are not friendly, and we just made ourselves a target. The realistic scenario is probably somewhere in between. That other civilizations, if they exist, are rare enough that we are not going to run into them anytime soon. That the galaxy is big, and even with warp drive, the distances are vast, and the odds of encountering anyone else are low. But low is not zero. And the moment we turn on a warp drive, we move from theoretical risk to actual risk. That is a threshold worth thinking about before we cross it. Assume the best case. Assume we build the warp drive, solve the political and ethical questions, reach another star, and find something worth finding. What does that do to humanity? Not in practical terms, in philosophical terms. For the entire history of our species, we have been confined to one planet. One tiny blue dot orbiting an average star in an unremarkable corner of the galaxy. Every human who has ever lived, every story, every war, every discovery, all of it happened here, on this rock, in this narrow band of atmosphere that keeps us alive. That confinement has shaped how we think about ourselves. We are small, isolated, alone in a universe that does not care whether we survive. Faster than light travel breaks that confinement. It turns the galaxy from a backdrop into a destination. It says we are not confined, we are not stuck. The universe is big, but it is not unreachable. And the moment we accept that, the moment we internalize it, everything changes, not immediately, not in a way you would notice day to day, but over generations the shift compounds. People grow up knowing that other stars are places you can go, not just points of light in the sky, that the galaxy is not a picture, it is a map, and maps have destinations. The psychological impact of that shift is hard to predict, but it is real. Humanity stops being a planetary species and starts being something else, something that does not have a word yet because we have never been it before. The species that left, that spread, that refused to stay in one place even when staying was easier and safer. That impulse, the drive to explore, to see what is over the next hill, has been part of us since before we were human. Faster than light travel does not create that impulse. It removes the last barrier preventing us from following it all the way to the edge of the galaxy and beyond. The road ahead is long. It is uncertain, and it does not promise success, but it exists. That is the shift the 2024 paper represents. Not that we have built a warp drive, that the road is there, that the physics allows it, that the engineering, impossible as it looks today, is not fundamentally blocked by the laws of the universe. We are standing at the beginning of that road, staring into the distance, trying to decide whether to start walking. The smart money says we will, because humanity has never seen a road and decided not to take it. We have climbed mountains that served no purpose except to prove we could. We have crossed oceans when we had no idea what was on the other side. We have left the planet and walked on the moon for no reason other than because it was there. The stars are there. The galaxy is there, and now, for the first time, there is a path, faint, difficult, littered with obstacles we have not even begun to map, but a path, and that is enough. It has always been enough. The question was never whether we would try. The question was whether the universe would let us. And the answer, tentative as it is yes. 25 trillion miles. That is still the distance to the nearest star. That number has not changed. What has changed is the period at the end of the sentence. For 3 decades, that period was final. The distance was too far. The physics were too hard. The exotic matter did not exist. The conversation was over before it began. Now the period is softer, not gone, but no longer quite so absolute. Because the wall we thought was solid turned out to have a crack, not wide enough to walk through. Not yet, but visible, measurable, real. The 2024 paper did not give us a starship. It gave us something rarer. Permission. Not from a government or a funding agency or a committee of skeptics. Permission from the universe itself. The equations that govern spacetime, the rules written into the fabric of reality, do not forbid this. They allow it, under conditions we do not yet know how to create, with energy we do not yet know how to generate, but allowed. And allowed is not the same as impossible. Humanity has spent its entire existence pushing against walls. Some of them fell, some of them bent. Some of them are still standing, waiting for better tools or smarter engineers or just more time. The speed of light has been a wall since 1905, a hard limit, a cosmic stop sign that every physicist pointed to when someone asked whether we could ever reach the stars in less than lifetimes. That wall is still there, but there is a door in it now, locked, heavy, guarded by problems we have not solved. But a door, and doors eventually open. The road is long, the timeline is uncertain, the obstacles are real, but we are walking, and we have never stopped walking. Not when the